In the vast expanse of the universe, there are galaxies so strange and powerful that they seem to defy the very laws of nature as we understand them. These galaxies are not just glowing balls of stars, they're cosmic powerhouses, emitting unimaginable amounts of energy in the form of radio waves. But there's something even more baffling about a particular class of galaxies, non-thermal radio galaxies. Unlike most galaxies, their radio emissions don't come from the heat of stars or traditional sources. Instead, these galaxies generate energy through mysterious, high-speed jets that stretch across millions of light years, creating massive structures far beyond our wildest expectations. What lies at the heart of these cosmic giants? How do their black holes unleash such incredible power? And what secrets are hidden in the radio waves they emit? Today, we're diving deep into one of the most enigmatic phenomena in the universe, one that has confounded scientists for decades and continues to challenge everything we think we know about space itself. Welcome to the strange and electrifying world of non-thermal radio galaxies. But before we continue, subscribe to the channel so you don't miss out on any of these videos. The study of non-thermal radio galaxies is far from simple. These galaxies often contain active supermassive black holes at their centers, which may play a major role in their unusual characteristics. The black holes within these galaxies can spew out jets of particles at near-light speeds, creating intense magnetic fields and producing vast amounts of radiation, including radio waves. These jets can stretch across millions of light years, making the radio emissions from these galaxies detectable even from Earth. But the mechanism behind how and why this energy is generated is still one of the greatest mysteries in astrophysics. One of the most puzzling aspects of non-thermal radio galaxies is their ability to produce this energy without relying on the thermal processes that most other galaxies depend on. In most galaxies, the heat generated by stars is what powers their emission of radiation, but in non-thermal radio galaxies, the source of energy isn't heat, it's high-speed, charged particles that are accelerated to mind-boggling speeds by powerful magnetic fields. These energetic particles then collide with surrounding matter, producing the radio waves that we can detect. The study of non-thermal radio galaxies has opened up a wealth of possibilities in terms of understanding the nature of galaxies, the behavior of supermassive black holes, and the way cosmic forces shape the universe. These galaxies don't just challenge our understanding of physics, they offer a glimpse into the forces at play in some of the most extreme environments in the universe. At the heart of most non-thermal radio galaxies is an active supermassive black hole. These black holes are typically millions, if not billions, of times the mass of our Sun. The immense gravitational pull of these black holes causes material to spiral inward, creating what is known as an accretion disk. As this material gets pulled into the black hole, it heats up, emitting X-rays and other forms of radiation. But what's truly remarkable about these galaxies is that they often produce enormous jets of particles that shoot out from the poles of the black hole, perpendicular to the accretion disk. These jets are made up of highly energetic particles, including electrons and protons, which are accelerated to relativistic speeds by the magnetic fields generated around the black hole. The energy in these jets doesn't come from the typical sources of heat, such as the burning of hydrogen in stars. Instead, it comes from the complex interactions between the magnetic fields around the black hole and the particles within the accretion disk. These interactions can accelerate particles to speeds close to that of light, creating what are known as non-thermal emissions. This is a stark contrast to the thermal emissions from stars, which are driven by the heat produced through nuclear fusion. In non-thermal radio galaxies, the emissions are generated by the kinetic energy of fast-moving particles, making them a fascinating subject of study for astrophysicists. The radio emissions from these galaxies can be detected using radio telescopes, and they often appear as bright, extended structures that stretch across vast regions of space. These emissions are sometimes referred to as radio lobes, and they can be found at the ends of the jets emitted by the supermassive black holes. These lobes are not caused by the thermal radiation emitted by stars, but rather by the high-energy particles in the jets interacting with the surrounding environment. The size of these lobes can be truly staggering, often stretching for millions of light years. In some cases, the lobes can even be larger than the host galaxy itself, providing a striking visual reminder of the immense power at play within these galaxies. One of the most intriguing aspects of non-thermal radio galaxies is how they can sometimes appear to be quieter than their thermal counterparts. While most galaxies emit radiation across the entire electromagnetic spectrum, non-thermal radio galaxies are often much more prominent in the radio wavelengths. This is due to the fact that their primary source of energy is the high-speed particles in the jets, rather than the heat produced by stars. As a result, these galaxies may appear to be less luminous in optical or infrared wavelengths, but their radio emissions can be far more intense. Interestingly, non-thermal radio galaxies can sometimes be classified into two main categories: Phaneroff-Rayleigh Class I and Class II. These two categories refer to the different ways in which the radio lobes appear. In Phaneroff-Rayleigh Class I galaxies, the radio lobes are relatively compact, with the radio emission being concentrated near the galaxy's core. In Phaneroff-Rayleigh Class II galaxies, the lobes are much more extended, with the radio emission spreading out across a much larger region of space. This difference in the appearance of the radio lobes is thought to be related to the strength of the magnetic fields around the black hole, as well as the speed at which the particles in the jets are moving. The study of non-thermal radio galaxies has important implications for our understanding of the evolution of galaxies and the role that supermassive black holes play in shaping their behavior. These galaxies are often seen as relics of an earlier time in the universe's history, when black holes were more actively accreting material and producing powerful jets. By studying these galaxies, astronomers can gain insight into the processes that shape the universe in its early stages, and how galaxies have evolved over billions of years. But the story of non-thermal radio galaxies doesn't end there. These galaxies also play a key role in the larger-scale structure of the universe. The energy released by the jets can have a profound impact on the surrounding environment, particularly in the intergalactic medium. As the jets interact with the gas and dust in the surrounding space, they can heat up and accelerate particles, creating large-scale shocks and turbulence. This can lead to the formation of giant bubbles of hot gas, which can have a significant effect on the distribution of matter in the universe. These interactions between non-thermal radio galaxies and their environments are crucial for understanding how galaxies influence the cosmic web and the large-scale structure of the universe. One of the most exciting developments in the study of non-thermal radio galaxies has been the discovery of more and more of these galaxies using advanced radio telescopes, such as the Very Large Array, VLA, and the Square Kilometer Array, SKA. These telescopes are able to detect the faint radio emissions from galaxies that are billions of light years away, providing a deeper understanding of the cosmic phenomena at play. With each new discovery, astronomers are piecing together the puzzle of how non-thermal radio galaxies fit into the broader picture of galaxy evolution and the dynamics of the universe. Non-thermal radio galaxies represent one of the most fascinating and mysterious phenomena in astrophysics. Their ability to emit vast amounts of energy in the form of radio waves, driven by the interactions between supermassive black holes and their surrounding environments, challenges our understanding of the universe. By studying these galaxies, astronomers can gain invaluable insights into the behavior of black holes, the evolution of galaxies, and the forces that shape the cosmos itself. As we continue to explore the depths of space and unravel the mysteries of the universe, non-thermal radio galaxies will undoubtedly remain a key piece of the puzzle, offering a window into the extreme environments that exist beyond our wildest imaginations. The study of non-thermal radio galaxies is not only crucial for understanding the immediate environments surrounding supermassive black holes, but it also plays a role in addressing fundamental questions about the nature of matter, energy, and the behavior of cosmic systems at the largest scales. One of the most remarkable aspects of non-thermal radio galaxies is their ability to challenge the standard understanding of how galaxies form, evolve, and interact with their surroundings. These galaxies, with their powerful jets and immense magnetic fields, provide a unique perspective on how energy is distributed across vast distances and how the influence of supermassive black holes can extend far beyond the galaxies they inhabit. To truly appreciate the significance of non-thermal radio galaxies, it's essential to understand the role they play in the broader cosmic environment. While these galaxies are relatively rare, they are far from insignificant in the grand scale of the universe. The energy released by their jets has the potential to affect the intergalactic medium, the vast regions of space between galaxies. The particles accelerated in the jets are not just limited to the immediate vicinity of the black hole. These high-energy particles travel outward, sometimes at speeds close to the speed of light, and can reach far beyond the galaxy, interacting with the gas and dust that fill the space between galaxies. The interaction of these particles with the intergalactic medium can have a profound impact on the evolution of galaxies, stars, and even the formation of new structures in the universe. As the jets from non-thermal radio galaxies collide with the surrounding gas, they can create shockwaves, compressing and heating the gas to extreme temperatures. This can trigger the formation of new stars or, in some cases, prevent star formation by heating the gas to such high temperatures that it becomes unable to cool and collapse to form new stars. These processes are an important piece of the puzzle when it comes to understanding the feedback mechanisms that shape the evolution of galaxies and the distribution of matter in the universe. Interestingly, the jets of non-thermal radio galaxies also interact with the so-called cosmic web, the vast network of filaments and voids that make up the large-scale structure of the universe. This cosmic web is the result of the gravitational pull of galaxies and clusters of galaxies, which have shaped the distribution of matter across the universe. The jets from non-thermal radio galaxies can influence this structure by adding additional energy to the intergalactic medium, possibly helping to shape the formation of these filaments and voids. The study of these interactions is still in its infancy, but it holds tremendous potential for advancing our understanding of the large-scale forces that govern the universe. Another fascinating aspect of non-thermal radio galaxies is their potential connection to galaxy clusters. Galaxy clusters are some of the largest structures in the universe, containing hundreds or even thousands of galaxies bound together by gravity. These clusters often contain enormous amounts of hot gas, which is heated by the gravitational forces at play within the cluster. Non-thermal radio galaxies are often found in or near these clusters, where their jets can interact with the hot gas, creating complex structures such as radio halos and radio relics. These structures are vast regions of radio emission that can stretch for millions of light years, often creating intricate patterns in the sky that astronomers are only beginning to understand. The radio halos and relics associated with non-thermal radio galaxies are not just interesting because of their size and complexity. They also provide valuable information about the conditions within galaxy clusters. These features can be used to probe the properties of the hot gas within clusters, including its temperature, density, and magnetic field strength. By studying these structures, astronomers can learn more about the processes that govern galaxy cluster dynamics and the role that non-thermal radio galaxies play in shaping the behavior of these massive cosmic structures. Non-thermal radio galaxies also offer important clues about the evolution of active galactic nuclei, AGN, the energetic centers of galaxies that host supermassive black holes. These AGN are thought to play a critical role in the growth and evolution of galaxies, with their powerful emissions shaping the environments of their host galaxies and influencing the formation of new stars. The study of non-thermal radio galaxies allows astronomers to investigate the relationship between AGN and their surrounding environments in greater detail. By understanding how the jets from supermassive black holes interact with the intergalactic medium and other structures in the universe, scientists can gain a deeper understanding of the feedback mechanisms that regulate galaxy growth and evolution. Moreover, the presence of non-thermal radio galaxies in different regions of the universe can provide important clues about the history of galaxy formation and the evolution of cosmic structures over time. For example, some non-thermal radio galaxies are observed in distant regions of the universe, where they appear to be in the early stages of their evolution. By studying these galaxies, astronomers can investigate how active supermassive black holes formed and began to power powerful jets in the early universe. These observations can shed light on the conditions that led to the formation of the first supermassive black holes, and how they evolved over time. As our understanding of non-thermal radio galaxies continues to evolve, new technologies and observational techniques are helping astronomers unlock even more mysteries. The development of more sensitive radio telescopes, such as the upcoming Square Kilometre Array (SKA), promises to revolutionize our ability to study these galaxies in unprecedented detail. The SKA, with its vast array of radio dishes, will be able to observe the faintest radio emissions from galaxies billions of light-years away, providing new insights into the behavior of non-thermal radio galaxies and their role in the evolution of the universe. The next few decades could see a dramatic increase in our understanding of these enigmatic objects, as astronomers continue to push the boundaries of what we know about the cosmos. One particularly exciting area of research is the study of high-redshift non-thermal radio galaxies. These galaxies, located at great distances from Earth, offer a glimpse into the universe's past. Because of the time it takes for their light to reach us, the radio emissions from these galaxies provide a snapshot of the universe at an earlier time, often when the universe was much younger. Studying high-redshift non-thermal radio galaxies can help astronomers understand how galaxies and supermassive black holes evolved in the early universe and how the cosmic structures we observe today came into being. Furthermore, the interaction between the jets of non-thermal radio galaxies and their environments can provide valuable information about the physical conditions of the universe during its infancy. For example, the jets from these galaxies can heat and accelerate particles in the surrounding gas, providing a window into the processes that occurred during the formation of the first large-scale cosmic structures. By studying these interactions, scientists can gain a better understanding of how galaxies, black holes, and cosmic structures evolved in the early universe. The unique properties of non-thermal radio galaxies also make them a powerful tool for testing theories about the nature of dark matter and dark energy. These mysterious substances, which make up most of the mass and energy in the universe, remain largely elusive to scientists. However, the way in which non-thermal radio galaxies interact with their environments could provide indirect evidence for the existence of dark matter and dark energy. For example, the distribution of radio emission in the jets of these galaxies may be influenced by the gravitational effects of dark matter, while the large-scale structure of the universe may be shaped by the mysterious forces of dark energy. Non-thermal radio galaxies are an essential part of the cosmic puzzle. Their unique properties, including the powerful jets of high-energy particles and the extended radio lobes that stretch across vast regions of space, offer critical insights into the behavior of supermassive black holes, the evolution of galaxies, and the interactions between galaxies and their environments. As our understanding of these galaxies grows, so too does our knowledge of the fundamental forces that shape the universe. From their role in galaxy formation and evolution to their potential connections to dark matter and dark energy, non-thermal radio galaxies are proving to be some of the most fascinating and important objects in modern astrophysics. As we continue to explore the mysteries of non-thermal radio galaxies, it's important to delve deeper into the mechanisms that drive the formation of their powerful jets. Understanding how these jets form and the forces at play in shaping them can provide us with critical insights not just into the nature of these galaxies, but also into the broader processes that govern the universe. The jets of non-thermal radio galaxies are composed primarily of charged particles, such as electrons and protons, which are accelerated to nearly the speed of light by the intense gravitational and magnetic forces around the supermassive black hole at the galaxy's center. But how exactly are these jets created, and what forces are responsible for their formation? The process begins in the accretion disk surrounding the supermassive black hole. The accretion disk is made up of gas and dust that spirals inward toward the black hole due to its immense gravitational pull. As this material gets closer to the event horizon, it heats up to incredibly high temperatures, emitting intense radiation across the electromagnetic spectrum. Some of this radiation is absorbed by the surrounding gas and particles, causing them to be accelerated to extremely high velocities. The next key component in jet formation is the magnetic field. As the gas spirals inward, the rotation of the black hole and the accretion disk can generate powerful magnetic fields. These fields become twisted and compressed as they move toward the black hole, and in some regions, they can channel the high-energy particles away from the black hole in the form of jets. These jets are highly collimated, meaning they are focused into narrow beams that can extend over vast distances, sometimes stretching millions of light-years from the galaxy's core. The magnetic field acts as a kind of conduit, guiding the accelerated particles along the axis of rotation, ensuring that the energy is expelled in the form of a jet rather than being dispersed in all directions. This magnetic jet formation process is still an area of active research, and new discoveries are being made with each new generation of telescopes and observational techniques. Theoretical models of jet formation continue to evolve, with some recent models suggesting that the material in the jets is not just accelerated by the black hole's gravity and magnetic fields, but also by turbulence and shock waves within the accretion disk itself. These processes may help to explain the wide variety of jet structures and behaviors observed in different types of non-thermal radio galaxies. The energy and material in the jets are not just expelled outward from the black hole for no reason. They play a significant role in the evolution of the host galaxy and its surrounding environment. The jets can have profound effects on the intergalactic medium, the vast, largely empty space between galaxies. As the particles in the jet travel outward, they interact with the gas and dust that fill this space, creating shock waves and heating the surrounding material. This can result in the formation of vast radio lobes, huge regions of radio emission that can stretch for millions of light years. These lobes are often observed in non-thermal radio galaxies, and their structure provides valuable insights into the processes at work in these galaxies. In addition to their role in heating the intergalactic medium, the jets of non-thermal radio galaxies also influence the process of star formation in their host galaxies. The energetic particles in the jets can compress the surrounding gas, triggering the formation of new stars. However, in some cases, the energy from the jets can be so intense that it prevents the gas from collapsing into stars, effectively quenching star formation. This delicate balance between star formation and jet-driven feedback is a crucial area of research, as it helps astronomers understand the factors that regulate the growth and evolution of galaxies. What's more, the study of non-thermal radio galaxies also provides key insights into the nature of the supermassive black holes that lie at their centers. These black holes, which can have masses millions or even billions of times that of our Sun, are some of the most extreme objects in the universe. By studying the jets emitted by these black holes, astronomers can learn more about their growth, behavior, and the surrounding environment. For example, the jets from these galaxies can be used to probe the dynamics of the accretion disk, the magnetic fields around the black hole, and the material in the surrounding gas. This information is essential for understanding how supermassive black holes influence their host galaxies and how they evolve over cosmic time. One of the most fascinating aspects of non-thermal radio galaxies is their sheer scale. The jets emitted by these galaxies are capable of stretching across vast distances, sometimes extending millions of light years from the galaxy's center. This makes non-thermal radio galaxies some of the largest known structures in the universe. The size and power of these jets are truly mind-boggling, and they highlight the immense forces at play in the most extreme regions of space. The enormous size of the radio lobes created by these jets also presents challenges for astronomers trying to study them. These lobes are often so large and diffuse that they can be difficult to detect with traditional radio telescopes. However, with the advent of new technologies such as the Square Kilometre Array, SKA, and the Event Horizon Telescope, EHT, astronomers are now able to observe these structures in greater detail than ever before. These cutting-edge telescopes have allowed scientists to explore the most distant and faintest regions of the universe, providing new insights into the nature of non-thermal radio galaxies and their jets. The future of non-thermal radio galaxy research is an exciting one. With each new discovery, we are learning more about the forces that drive the formation and evolution of galaxies, the behavior of supermassive black holes, and the interactions between galaxies and the broader cosmic environment. As we continue to develop more advanced observational techniques and technologies, we will be able to study these fascinating objects in even greater detail, unlocking new mysteries of the universe in the process. One particularly intriguing area of research is the connection between non-thermal radio galaxies and the formation of large-scale cosmic structures such as galaxy clusters. Galaxy clusters are the largest gravitationally bound structures in the universe, and they contain vast amounts of gas, stars, and dark matter. The jets from non-thermal radio galaxies can influence the evolution of these clusters by injecting energy into the intergalactic medium. This process can lead to the formation of large-scale structures like radio relics and halos, which can provide valuable insights into the dynamics of galaxy clusters and the properties of the gas that fills them. Moreover, the study of non-thermal radio galaxies is helping to advance our understanding of the broader processes that shape the universe. For example, by observing the interactions between these galaxies and the intergalactic medium, astronomers can learn about the processes that govern the distribution of matter in the universe. They can also gain insights into the behavior of dark matter and dark energy, two of the most mysterious and elusive substances in the cosmos. As our ability to observe these objects improves, we can expect to uncover even more surprises that will challenge our understanding of the universe. Non-thermal radio galaxies are one of the most exciting and important objects in modern astrophysics. These galaxies, with their powerful jets and vast radial lobes, provide a unique window into the workings of the universe at the largest scales. From their role in shaping the intergalactic medium to their influence on galaxy formation and evolution, non-thermal radio galaxies are helping to answer some of the most fundamental questions in astronomy. As our understanding of these fascinating objects continues to evolve, we can be sure that they will continue to provide valuable insights into the nature of the universe and our place within it. As we continue our exploration of non-thermal radio galaxies, it's essential to touch upon the broader implications of their study on our understanding of the cosmos. These galaxies provide a glimpse into the most extreme and energetic environments in the universe, revealing processes that operate on scales that are both mind-boggling and fascinating. One of the most significant aspects of non-thermal radio galaxies is the interplay between the energetic jets they produce and the surrounding cosmic environment. This interaction not only has profound effects on the galaxies themselves but also on the larger structures that they inhabit. One of the areas where non-thermal radio galaxies are making a significant impact is in the study of galaxy cluster evolution. Galaxy clusters are immense gravitationally bound systems that contain hundreds or even thousands of galaxies. These clusters are the largest structures in the universe held together by gravity. However, while galaxy clusters may seem like relatively stable systems, they are far from static. They are constantly evolving and undergoing dramatic changes due to various cosmic processes. The jets of non-thermal radio galaxies play a key role in this evolution by injecting vast amounts of energy into the intergalactic medium, the diffuse gas that exists between galaxies in a cluster. This energy input from the jets can have a variety of effects on the galaxy cluster. One of the most significant outcomes is the heating of the intracluster medium, which is the hot gas that fills the space between the galaxies. The energy from the jets can heat this gas to extremely high temperatures, creating a feedback loop that regulates the overall growth and behavior of the cluster. This process, known as feedback heating, is essential for understanding how galaxy clusters evolve over time. Without this feedback, the gas in galaxy clusters would cool down and condense, leading to an excess of gas in the central regions of the cluster. This would trigger excessive star formation, ultimately disrupting the balance of the cluster and causing it to become less stable. The energy deposited by the jets can also lead to the formation of large-scale structures within the galaxy cluster. One of the most striking features that result from this interaction is the formation of radio relics and halos. These structures are massive regions of radio emission that can stretch for millions of light-years. They are created when the jets from non-thermal radio galaxies interact with the surrounding gas, creating shockwaves and turbulence that generate radio waves. The formation of these relics and halos is not only fascinating in itself, but it also provides valuable insights into the dynamics of galaxy clusters and the processes that govern their evolution. The study of non-thermal radio galaxies also contributes to our understanding of the relationship between these galaxies and the central supermassive black holes that power them. Supermassive black holes are the engines driving the jets in non-thermal radio galaxies, and by studying the behavior of these black holes, astronomers can learn more about the processes that occur in their immediate vicinity. The interaction between the jets and the black hole is a delicate balance, with the gravitational forces of the black hole funneling material toward it while the jets expel high-energy particles outward. This interplay can offer critical clues about the formation and evolution of supermassive black holes and how they influence their host galaxies. The energy released by the jets in non-thermal radio galaxies can be so intense that it can actually affect the formation of new stars and the surrounding gas. In some cases, the energy from the jets can prevent the gas from cooling and condensing into stars, effectively halting star formation. This process is known as jet feedback, and it plays a critical role in the regulation of star formation within galaxies. In galaxies where the jets are particularly powerful, they can suppress star formation to such an extent that the galaxy becomes quenched or inactive, unable to produce new stars for billions of years. On the other hand, in some non-thermal radio galaxies, the jets may have the opposite effect, stimulating star formation in the surrounding gas. The shockwaves and turbulence created by the jets can compress the gas, triggering the collapse of regions of the gas cloud into new stars. This process is known as jet-induced star formation, and it has been observed in several non-thermal radio galaxies. These galaxies provide a unique laboratory for studying the complex interactions between active galactic nuclei, AGN, supermassive black holes, and the processes that regulate star formation. While the energy released by the jets of non-thermal radio galaxies can have profound effects on star formation, it can also influence the evolution of the host galaxy in other ways. For example, the outflow of energy from the jets can cause the surrounding gas to expand, altering the structure of the galaxy. This can lead to changes in the distribution of stars and gas within the galaxy, as well as the overall shape and size of the galaxy. In some cases, the energy from the jets may even trigger the formation of new structures, such as galactic halos or bulges. One of the most exciting aspects of studying non-thermal radio galaxies is the potential to learn about the broader processes that govern the universe. These galaxies, with their immense power and intricate structures, provide a natural laboratory for investigating the behavior of matter and energy in extreme environments. By studying the jets, magnetic fields, and accretion disks of non-thermal radio galaxies, astronomers can gain valuable insights into the workings of supermassive black holes, the formation of large-scale structures, and the evolution of galaxies over cosmic time. The role of non-thermal radio galaxies in the larger cosmic picture is not limited to their immediate environment. Their jets, and the energy they release, can have far-reaching consequences on a much larger scale. For example, the jets of non-thermal radio galaxies can contribute to the heating and acceleration of particles in the intergalactic medium, the vast expanse of space that exists between galaxies. This energy input can have a profound impact on the evolution of the cosmic web, the large-scale structure of the universe that consists of galaxies, gas, and dark matter. The study of non-thermal radio galaxies also provides critical insights into the fundamental nature of the universe itself. For example, the powerful jets emitted by these galaxies may be able to accelerate particles to energies far beyond what we can achieve in particle accelerators on Earth. This makes non-thermal radio galaxies invaluable for studying the behavior of particles under extreme conditions, helping to bridge the gap between astrophysics and particle physics. The high-energy particles in these jets may also be able to provide clues about the nature of dark matter and dark energy, two of the most mysterious substances in the universe. Non-thermal radio galaxies represent one of the most captivating and enigmatic areas of astrophysical research. The immense power of their jets, the role they play in the evolution of galaxies, and their connection to supermassive black holes make them essential to our understanding of the universe. As our observational technologies continue to improve, we are likely to uncover even more secrets about these fascinating objects. From their influence on galaxy cluster evolution to their impact on star formation, non-thermal radio galaxies are offering us a glimpse into the most extreme environments in the universe. And in doing so, they are helping to shape our understanding of the cosmos itself. As we delve deeper into the study of non-thermal radio galaxies, it's crucial to understand the broader implications they have for the understanding of the universe. These galaxies serve as cosmic laboratories that allow astronomers to explore fundamental physics in some of the most extreme conditions imaginable. While we often focus on the grand scale of their jets and accretion disks, the smaller, more intricate details are equally important in revealing the mechanics at work within these galaxies. The study of non-thermal radio galaxies thus becomes an essential piece of the puzzle when it comes to deciphering the nature of the cosmos. One of the most intriguing aspects of non-thermal radio galaxies is their connection to large-scale cosmic phenomena. Their jets are not just isolated features. They interact with the surrounding cosmic structures, leaving their imprint on galaxy clusters, superclusters, and even the large-scale cosmic web. These interactions can drive the evolution of the universe itself, affecting the growth and distribution of galaxies and the formation of new stars and elements. At the center of every non-thermal radio galaxy lies a supermassive black hole, the powerhouse behind the energetic jets. These black holes are capable of ejecting material at speeds approaching the speed of light, creating jets that extend over vast distances, sometimes millions of light years. This extraordinary phenomenon raises questions about the processes that occur around these supermassive black holes, as well as the physical mechanisms that allow them to produce such immense energy. The relationship between the black hole, its accretion disk, and the surrounding environment is still a subject of active research, and new discoveries are constantly being made. One significant aspect of this research involves the study of the accretion process. The accretion disk surrounding a supermassive black hole is composed of gas and dust that spirals inward, heating up as it gets closer to the event horizon. The friction within the accretion disk generates tremendous amounts of heat and radiation, contributing to the creation of the jets. However, the precise mechanisms behind the jet formation are still not entirely understood. It's clear that magnetic fields play a crucial role in this process, with the twisting and folding of magnetic lines helping to channel the material away from the black hole and into the jets. The magnetic fields in non-thermal radio galaxies are also a key factor in their study. These fields are responsible for accelerating charged particles to relativistic speeds, creating the high-energy radiation that characterizes these galaxies. The intricate structure of these magnetic fields is still a subject of intense research. Some theories suggest that the fields are organized into large-scale structures, which help channel the jets along specific paths. Others propose that turbulence within the accretion disk might give rise to chaotic magnetic fields, creating a more complex environment that drives the production of the jets. One of the most exciting areas of research in the study of non-thermal radio galaxies is the investigation of their cosmic evolution. These galaxies are often found in some of the most distant parts of the universe, meaning that we are observing them at various stages of their development. By studying their radio emissions and jet structures, astronomers can piece together the history of galaxy formation and evolution. This can help answer some of the most fundamental questions about the origins of galaxies and the processes that drive their growth. The energy output from non-thermal radio galaxies also has significant implications for the study of the intergalactic medium, IGM. The IGM is the vast, largely invisible space between galaxies, filled with low-density gas and plasma. The jets from non-thermal radio galaxies can inject energy into this medium, causing it to heat up and become more turbulent. This can affect the distribution of matter across vast cosmic scales, influencing the formation of new galaxies and star systems. The energy from these jets may also be responsible for maintaining the temperature of the IGM, preventing it from cooling and condensing into dense clouds of gas. One aspect of the IGM that has garnered significant interest in recent years is the role of cosmic magnetic fields. These magnetic fields are thought to permeate the entire universe, stretching across the vast expanse between galaxies and clusters. The jets from non-thermal radio galaxies can contribute to the amplification of these cosmic magnetic fields, which in turn can influence the formation of large-scale structures in the universe. This process of magnetic field amplification is a relatively new area of study, and it holds the potential to reveal important insights into the evolution of the universe on a cosmological scale. The study of non-thermal radio galaxies also provides a unique opportunity to explore the relationship between galaxies and the mysterious substance known as dark matter. Dark matter, which makes up around 27% of the universe's mass, does not interact with light, making it extremely difficult to detect. However, its gravitational effects on visible matter are observable, and it is thought to play a crucial role in galaxy formation. The interaction between the jets from non-thermal radio galaxies and the dark matter and their surrounding environment could offer important clues about the properties of dark matter and its role in the evolution of galaxies. Another fascinating aspect of non-thermal radio galaxies is their potential as cosmic laboratories for studying high-energy particle physics. The particles accelerated in the jets of these galaxies can reach energies that far exceed anything achieved by human-made particle accelerators. By studying the interactions of these high-energy particles, scientists can gain valuable insights into the fundamental laws of physics. For example, the study of the cosmic rays produced by non-thermal radio galaxies could help to answer questions about the nature of dark matter, the origin of cosmic rays, and the behavior of matter at extreme temperatures and pressures. In addition to the scientific value of non-thermal radio galaxies, they also raise philosophical and existential questions about the nature of the universe. The extreme environments they represent challenge our understanding of the laws of physics and the limits of scientific knowledge. How do the forces at play within these galaxies compare to the fundamental forces that govern the rest of the cosmos? What can the study of these galaxies teach us about the nature of space, time, and matter itself? As we continue to study these cosmic giants, we are forced to confront some of the deepest questions about the universe, its origins, and its ultimate fate. Non-thermal radio galaxies are not only a captivating subject of study, but they also provide a window into the most extreme and energetic processes in the universe. From their interaction with the intergalactic medium to their impact on galaxy cluster evolution, these galaxies play a key role in shaping the large-scale structure of the cosmos. As our observational techniques continue to improve, we will undoubtedly uncover even more mysteries about these enigmatic objects. Whether it's the behavior of supermassive black holes, the role of magnetic fields, or the influence of cosmic jets on galaxy evolution, non-thermal radio galaxies are opening new doors to understanding the universe at a fundamental level. As we continue our exploration of non-thermal radio galaxies, it's important to note how the scientific community's growing understanding of these objects is reshaping our perspective on cosmic phenomena. These galaxies are not isolated or static features in the universe. Instead, they act as dynamic participants in an ever-evolving cosmic narrative. Every new discovery adds another layer to our comprehension of the forces that govern galaxies, black holes, and the space in between. It's a journey into the unknown, with every observation potentially unveiling new physics, challenging old theories, and offering a deeper glimpse into the heart of the universe. When we speak about the importance of non-thermal radio galaxies in the context of modern astronomy, we cannot overlook the technological advancements that have made these studies possible. In the past, our understanding of these galaxies was limited by the instruments available to us. But with the advent of radio telescopes such as the Very Large Array, VLA, the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Square Kilometer Array, SKA, astronomers are now able to probe these objects with unprecedented clarity and sensitivity. These instruments allow us to observe radio emissions from non-thermal radio galaxies with extreme precision, revealing not only the structure of the jets but also the fine details of the magnetic fields and particle acceleration processes occurring in these far-off cosmic realms. Radio telescopes, unlike optical telescopes, have the ability to peer through the dense clouds of gas and dust that often obscure our view of the more visible parts of the universe. This is especially important when studying objects like non-thermal radio galaxies, where the energetic jets and associated phenomena are often hidden from view in visible wavelengths. By capturing radio emissions, astronomers can study the behavior of these galaxies in ways that were previously impossible. It is through this lens that we are beginning to see the true scope and complexity of non-thermal radio galaxies. These advancements have allowed astronomers to refine their models of how the jets in non-thermal radio galaxies behave and evolve. The jets are not static, nor are they simple in nature. Over time, they expand, interact with surrounding material, and sometimes even form large-scale structures that span entire clusters of galaxies. Observing these jets in such fine detail has revealed that they are far more complex than previously thought. They can undergo dramatic changes in shape, velocity, and energy output, all depending on the local environment, the magnetic fields, and the physical conditions within the galaxy. Additionally, the study of non-thermal radio galaxies has illuminated the intricate relationships between different types of galaxies. For instance, it's been shown that these radio-emitting galaxies are often found in dense environments, such as galaxy clusters, where interactions between galaxies are common. These environments play a critical role in shaping the evolution of the radio galaxies, especially in terms of how their jets evolve and how the energy they emit interacts with the surrounding matter. The feedback between galaxies and the intergalactic medium can have profound implications for our understanding of galaxy formation, star formation, and the overall evolution of cosmic structures. But the insights we gain from these galaxies extend far beyond understanding the processes occurring in their immediate environment. By studying non-thermal radio galaxies, scientists are also exploring fundamental questions about the nature of cosmic evolution. For instance, the mechanisms that produce the immense amounts of energy observed in the jets of these galaxies can inform our understanding of energy generation on the largest scales. The accretion of matter onto supermassive black holes, combined with the resulting magnetic fields and particle acceleration, serves as a natural laboratory for investigating energy production, matter distribution, and the interplay between different forms of energy in the universe. Even more intriguingly, these galaxies serve as laboratories for studying exotic matter, including dark matter. While dark matter itself is invisible and difficult to detect directly, its presence can be inferred from the gravitational effects it exerts on surrounding matter. Non-thermal radio galaxies, with their energetic jets and complex structures, may provide indirect clues about the properties of dark matter and its interactions with visible matter. Understanding how dark matter may influence, or be influenced by the jets and magnetic fields of these galaxies could help scientists unlock some of the universe's most profound mysteries. Theoretical models surrounding non-thermal radio galaxies also provide fascinating insights into the physics of high-energy phenomena. The relativistic jets and their interactions with magnetic fields create a testbed for understanding particle dynamics under extreme conditions. These phenomena provide an ideal environment to study the behavior of matter and energy in regimes far beyond what we can recreate in laboratories here on Earth. For example, the acceleration of particles to relativistic speeds in the vicinity of supermassive black holes challenges our understanding of high-energy particle physics and allows us to study fundamental processes such as shock acceleration, synchrotron radiation, and inverse Compton scattering. Furthermore, the study of non-thermal radio galaxies has wide-reaching implications for the understanding of cosmic feedback mechanisms. These mechanisms refer to the ways in which galaxies, black holes, and the surrounding intergalactic medium interact in a cycle that can have profound effects on galaxy evolution. For instance, the jets produced by supermassive black holes in non-thermal radio galaxies can inject energy into the surrounding gas, preventing it from cooling and collapsing into new stars. This process of feedback can regulate the growth of galaxies, helping to shape the population of galaxies in the universe. Interestingly, this feedback mechanism can also impact the size and shape of galaxy clusters. The energy emitted by non-thermal radio galaxies can have a significant effect on the intergalactic medium, especially in dense environments like galaxy clusters. The jets from these galaxies can heat up the gas in the cluster, preventing the formation of new stars and altering the distribution of matter. Understanding these processes can help astronomers refine their models of galaxy cluster formation and evolution, providing a clearer picture of how the universe has evolved over time. As we continue to observe these galaxies, the importance of non-thermal radio galaxies in the broader context of the universe only becomes more apparent. These galaxies, with their energetic jets and powerful central black holes, are not isolated phenomena. They are part of a larger cosmic ecosystem, where interactions between galaxies, the intergalactic medium, and dark matter shape the universe as a whole. By studying these objects, we gain insights not only into the fundamental physics of the universe but also into the large-scale processes that drive its evolution. Moreover, the role of non-thermal radio galaxies extends to their impact on cosmological models. The interactions between galaxies, black holes, and the intergalactic medium challenge our current understanding of cosmic structure formation. These interactions also raise questions about the role of magnetic fields, dark matter, and cosmic radiation in the larger universe. With every new discovery, scientists are forced to rethink their models and refine their understanding of the cosmos. Non-thermal radio galaxies are more than just fascinating cosmic objects. They are key players in the evolution of the universe itself. Their energetic jets, powerful black holes, and intricate magnetic fields provide valuable insights into the workings of the cosmos on both large and small scales. As technology continues to advance, and as astronomers push the boundaries of our knowledge, we can expect even more groundbreaking discoveries in the study of non-thermal radio galaxies. Their study will continue to shape our understanding of the universe, challenging old paradigms and opening new frontiers of knowledge. By studying these galaxies, we are not just observing distant phenomena. We are exploring the very forces that govern the structure and evolution of the universe. The journey is ongoing, and with each discovery, we move closer to understanding the fundamental workings of the cosmos. As we continue to probe the depths of non-thermal radio galaxies, we encounter an array of phenomena that reveal the complexities of these cosmic entities. The deeper we venture, the more we realize that non-thermal radio galaxies offer not only a glimpse into the violent, energetic processes occurring at the centers of galaxies, but also a window into the evolution of the universe itself. These galaxies are, in a way, time capsules, holding clues to cosmic events that occurred billions of years ago. By studying them, we can unravel the mystery of how galaxies evolve, how their supermassive black holes shape their destinies, and how the very fabric of the universe behaves on the largest scales. To truly appreciate the significance of non-thermal radio galaxies, we need to understand the mechanisms that drive the formation of their powerful jets. At the heart of these galaxies lies a supermassive black hole, millions or even billions of times the mass of our Sun. The black hole's immense gravity draws in surrounding matter, including gas, dust, and even stars, creating an accretion disk. As matter spirals into the black hole, it heats up to extreme temperatures and emits large amounts of radiation, including X-rays and gamma rays. However, not all of the material in the accretion disk falls directly into the black hole. Some of it is channeled along magnetic field lines and expelled at near-light speeds in the form of relativistic jets. These jets are the defining feature of non-thermal radio galaxies. Unlike thermal radiation, which is generated by the motion of particles in hot gases, non-thermal radiation is produced by relativistic particles moving at speeds close to the speed of light. These particles interact with magnetic fields, creating a variety of high-energy phenomena, including synchrotron radiation, which is emitted in the radio spectrum. The synchrotron radiation from non-thermal radio galaxies is a key signature that astronomers use to identify these objects. The radiation can be detected across vast distances, allowing us to observe galaxies that are billions of light-years away. The composition and behavior of the jets in non-thermal radio galaxies can vary significantly depending on the specific conditions in the galaxy. For example, some jets are highly collimated, forming narrow, focused beams of energy that extend for millions of light-years. Others may be more diffuse and irregular in shape. The length and structure of the jets can provide important clues about the underlying processes driving them. In some cases, the jets are seen interacting with the intergalactic medium, creating shock waves and heating up surrounding gas. This interaction can influence the formation of stars, the growth of galaxies, and the overall evolution of cosmic structures. In addition to their high-energy jets, non-thermal radio galaxies also exhibit other intriguing features, such as powerful lobes of gas and plasma. These lobes are formed by the interaction of the jets with the surrounding medium, and they can extend tens of thousands of light-years away from the galactic core. The lobes are typically filled with relativistic particles and magnetic fields, which radiate in the radio wavelengths. In some cases, the lobes are so large that they become the dominant feature of the galaxy, overshadowing the galactic core itself. These lobes can be incredibly energetic, and their study has provided valuable insights into the processes of particle acceleration, cosmic magnetic fields, and the feedback mechanisms that regulate galaxy growth. The study of non-thermal radio galaxies has also revealed a variety of exotic phenomena. For instance, astronomers have observed radio galaxies with wide-angle tails, WATs, where the jets from the black hole are bent at large angles due to the influence of the surrounding medium. This phenomenon suggests that the gas in the region around the galaxy is not uniform, and that the jets are being deflected by large-scale magnetic fields or by interactions with other galaxies in the cluster. Another intriguing phenomenon is the X-shaped Radio Galaxies, where the jets appear to form an X shape, suggesting complex interactions between the jets and the surrounding gas. These unusual structures challenge our understanding of how the jets are generated and how they interact with their environments. What's even more fascinating is the fact that non-thermal radio galaxies can exist in diverse environments across the universe. They are found not only in the cores of massive galaxy clusters but also in more isolated settings, suggesting that the processes that drive their formation are not confined to any single type of cosmic environment. This diversity underscores the complexity of the mechanisms that govern galaxy formation and evolution. Some non-thermal radio galaxies are found in regions of the universe that are rich in dark matter, while others reside in areas with relatively low dark matter densities. This raises important questions about the role of dark matter in galaxy evolution and whether it has any direct influence on the formation and behavior of the jets. As astronomers continue to investigate non-thermal radio galaxies, they are also working to understand how these galaxies fit into the broader picture of cosmic evolution. The study of these galaxies has profound implications for our understanding of galaxy formation, black hole physics, and the behavior of matter in extreme environments. One of the key questions is how the energy from the jets and lobes affects the surrounding galaxy and its ability to form new stars. In some cases, the jets from the central black hole may inject so much energy into the surrounding gas that it prevents the formation of new stars, a process known as radio mode feedback. This feedback can regulate the growth of galaxies, potentially preventing them from becoming overly massive and ensuring that star formation remains in balance with other processes in the galaxy. Another important aspect of non-thermal radio galaxies is their potential role in the broader cosmic landscape. Some scientists hypothesize that these galaxies may play a significant role in the reionization of the universe, an event that occurred billions of years ago when the universe transitioned from a state of opacity to transparency. During this period, the first stars and galaxies began to form, and their ultraviolet radiation ionized the hydrogen gas that filled the universe. It's possible that the energetic jets from non-thermal radio galaxies may have contributed to this process by injecting large amounts of energy into the intergalactic medium, helping to ionize the gas and make the universe transparent to light. The study of non-thermal radio galaxies also has practical applications in the field of cosmology. By understanding the processes that occur within these galaxies, scientists can develop more accurate models of the large-scale structure of the universe. The jets from these galaxies can provide important clues about the distribution of matter and energy in the universe, including the role of dark matter and dark energy. Furthermore, by studying the way in which these galaxies interact with the surrounding intergalactic medium, astronomers can gain insights into the nature of the space between galaxies and how it has evolved over cosmic time. In the quest for a deeper understanding of the universe, non-thermal radio galaxies serve as essential tools for exploring some of the most fundamental questions in astrophysics. From the nature of black holes to the role of magnetic fields, from particle acceleration to cosmic evolution, these galaxies provide valuable clues that are essential to our understanding of the cosmos. With each new observation and discovery, we move closer to unlocking the mysteries of the universe, and the study of non-thermal radio galaxies will undoubtedly continue to play a central role in this exciting journey of exploration. As we delve even deeper into the complex world of non-thermal radio galaxies, we begin to uncover the vast variety of phenomena and mysteries that these enigmatic objects present. They are not simply oddities in the sky, they are critical pieces in the puzzle of the universe's history. Their study reveals much about the forces at play in the most extreme regions of space, and their behavior challenges our understanding of physics and astrophysics at the largest scales. One of the key reasons why non-thermal radio galaxies are so interesting is the incredible power they exhibit. These galaxies often host supermassive black holes that are millions to billions of times the mass of our Sun, and these black holes are the primary drivers behind the energetic jets and lobes that characterize non-thermal radio galaxies. The jets, formed by material in the accretion disk being accelerated to relativistic speeds, emit powerful radiation as they travel outward, colliding with surrounding gas and dust, as well as the intergalactic medium. This radiation is typically seen in the radio, optical, and even X-ray wavelengths, and it provides astronomers with a unique opportunity to observe some of the most energetic processes in the universe. In a sense, the jets and lobes of non-thermal radio galaxies act as cosmic laboratories, allowing us to study the behavior of relativistic particles, magnetic fields, and high-energy processes in environments that are far more extreme than anything we encounter on Earth. These phenomena are not just fascinating in their own right, they have far-reaching implications for understanding the very nature of the universe. For instance, studying the magnetic fields around these galaxies can give us insights into the formation and evolution of large-scale cosmic structures. The high-energy particles found in the jets offer a window into the physics of particle acceleration, while the interactions between the jets and the surrounding gas provide clues about the processes that regulate galaxy formation and evolution. The diversity of non-thermal radio galaxies is also a key feature that makes them so intriguing. While many are found in the cores of galaxy clusters, others are more isolated. Some may exhibit highly collimated jets, while others show more diffuse, irregular jets. These differences provide valuable insights into the various environments in which these galaxies exist, as well as the underlying processes that drive the formation of their jets. In particular, the study of the jet structures and their interactions with the surrounding gas has become one of the most active areas of research in modern astrophysics. One of the most exciting aspects of non-thermal radio galaxies is their potential to reveal hidden aspects of the universe, such as the role of dark matter and dark energy. These galaxies often exist in regions where the distribution of matter is still not fully understood, such as the outskirts of galaxy clusters or in regions with a high concentration of dark matter. By studying the behavior of non-thermal radio galaxies in these environments, scientists can begin to unravel the mystery of dark matter, a substance that makes up a significant portion of the universe's mass but has so far been invisible to our instruments. Equally important is the potential for non-thermal radio galaxies to shed light on the processes of galaxy evolution. These galaxies can act as laboratories for studying the feedback mechanisms that regulate galaxy growth. As mentioned earlier, the energetic jets emitted by the central black hole can inject large amounts of energy into the surrounding gas, which can suppress or enhance star formation. This feedback process is crucial for understanding how galaxies evolve over time. Some models suggest that the energy from these jets could play a key role in regulating the balance between gas cooling and star formation, potentially preventing galaxies from becoming too massive or too small. The jets may even play a role in the process of galaxy quenching, where star formation slows or ceases altogether. Another fascinating aspect of non-thermal radio galaxies is their potential role in the large-scale structure of the universe. The jets from these galaxies can influence the intergalactic medium, affecting the distribution of gas and matter on cosmic scales. In some cases, the energy from these jets may help to stir up the gas between galaxies, triggering the formation of new structures or influencing the flow of matter across vast distances. This kind of feedback could play a crucial role in shaping the overall evolution of the universe. Additionally, as these jets extend across vast distances, they can provide valuable information about the nature of the intergalactic medium and the magnetic fields that permeate it. An interesting feature of some non-thermal radio galaxies is their ability to produce large-scale shock waves. These shocks are created when the jets travel through the surrounding gas at speeds greater than the speed of sound. The shock waves can accelerate particles to relativistic speeds, creating high-energy cosmic rays that can radiate in the radio, optical, and X-ray wavelengths. These shock waves can also compress and heat the surrounding gas, potentially triggering the formation of new stars or influencing the growth of galaxies. The study of these shock waves has become an important aspect of understanding the role of non-thermal radio galaxies in the broader cosmic landscape. In recent years, astronomers have been using increasingly sophisticated techniques to study non-thermal radio galaxies. For example, the use of high-resolution radio telescopes, such as the Very Large Array, VLA, and the Atacama Large Millimeter/Submillimeter Array, ALMA, has allowed researchers to observe these galaxies in unprecedented detail. These instruments provide a clearer picture of the jets, lobes, and other features of non-thermal radio galaxies, enabling astronomers to map out the distribution of matter and energy within these galaxies with greater precision than ever before. Another exciting development in the study of non-thermal radio galaxies is the application of advanced simulations. With the help of supercomputers, scientists are now able to simulate the behavior of jets and lobes in a variety of environments, from the cores of galaxy clusters to more isolated regions of space. These simulations are helping to test theories about the formation and evolution of non-thermal radio galaxies, as well as the physical processes that govern their behavior. They are also shedding light on the interaction between the jets and the surrounding gas, helping to explain the complex structures observed in these galaxies. In addition to their importance in astrophysics, non-thermal radio galaxies also hold potential for understanding broader cosmological questions. For instance, the study of these galaxies may provide clues about the early universe, especially the period known as the Cosmic Dawn. During this time, the first stars and galaxies were forming, and it is possible that non-thermal radio galaxies played a role in reionizing the universe, making it transparent to light for the first time. By studying the evolution of these galaxies, astronomers can gain insights into the conditions that prevailed in the early universe and the processes that led to the formation of the structures we observe today. Moreover, non-thermal radio galaxies are also key objects for testing fundamental theories of physics, particularly those related to the behavior of matter and energy in extreme environments. The jets and magnetic fields found in these galaxies offer a natural laboratory for studying the effects of relativistic speeds, strong magnetic fields, and high-energy particle interactions. As we continue to study these galaxies, we may uncover new insights into the fundamental forces that govern the universe and the nature of space-time itself. As our technology improves and our understanding of non-thermal radio galaxies continues to grow, these fascinating objects will remain central to our quest to understand the universe. The mysteries of their powerful jets, their complex interactions with the intergalactic medium, and their role in the evolution of galaxies will continue to inspire astronomers and astrophysicists for many years to come. From the formation of massive black holes to the acceleration of particles to near-light speeds, the study of non-thermal radio galaxies provides an essential piece of the puzzle that will ultimately reveal the true nature of the cosmos. As we continue our exploration of non-thermal radio galaxies, it becomes clear that their complexity goes far beyond what can be initially observed. The deeper we dig into their behavior and impact on the surrounding universe, the more intricate and fascinating their influence becomes. One of the key aspects that make non-thermal radio galaxies so intriguing is the way their jets interact with the environment. These jets, formed by material being expelled from the supermassive black hole at the center of the galaxy, can stretch across vast distances, sometimes even larger than the host galaxy itself, completely transforming the intergalactic medium around them. The energy output from these jets is so immense that it can affect the distribution of gas and particles in the surrounding areas, leading to a process known as feedback. This feedback can have significant implications for galaxy evolution. When jets of relativistic particles collide with gas, it can heat and compress the gas, which can either trigger or suppress star formation. The feedback process is believed to be crucial in regulating the size and star formation rate of galaxies. Without this mechanism, galaxies might grow too quickly or become too starved of gas, which could prevent the development of stable systems. One of the most fascinating consequences of the interaction between jets and their environment is the creation of large-scale cosmic structures. These radio galaxies act as powerful cosmic engines that shape the intergalactic medium, and may even play a role in the large-scale organization of the universe. The lobes, which extend from the jets, often contain an immense amount of energy that can reach across millions of light-years, essentially molding the fabric of space around them. These massive structures could help in understanding how galaxies form, evolve, and interact with one another in the broader universe. The discovery of these extended lobes, often associated with large radio galaxies, has revealed something else of great importance: the relationship between different types of galaxies. Non-thermal radio galaxies, especially those with powerful jets, often exist in regions where there are dense clusters of galaxies. It is believed that these radio galaxies are key players in the growth and evolution of galaxy clusters. The jets can help shape the gas in these regions, while also playing a part in galaxy mergers and interactions, which are fundamental processes in the evolution of the universe's largest structures. The fact that non-thermal radio galaxies can exist in such a variety of environments, from dense clusters to more isolated regions, only adds to the complexity of the picture. These galaxies exhibit a range of behaviors depending on their surroundings, which makes them an invaluable tool for understanding the different phases of galaxy evolution. Some radio galaxies, for example, show signs of intense activity in their central black holes, while others exhibit more quiescent behavior, suggesting that the activity of the black hole might be regulated by the amount of surrounding gas and matter. One of the more unusual aspects of these galaxies is the way in which their jets can seem to operate in bipolar configurations. This means that the jets often emit in opposite directions from the center of the galaxy, forming two massive lobes on either side of the central black hole. This symmetric jet formation is a characteristic feature of many non-thermal radio galaxies and has been the subject of much study. The origin of this symmetry is not fully understood, but it may be related to the way in which material is funneled into the black hole, as well as the behavior of the surrounding magnetic fields. In fact, the role of magnetic fields in shaping these jets is an area of active research, as the interaction between the material and the magnetic fields could provide insights into the nature of these powerful jets. Moreover, the intensity of these jets is closely linked to the power of the central black hole. Supermassive black holes, which can range from millions to billions of solar masses, are the engines that drive these high-energy jets. As matter falls into the black hole, it forms a hot, rotating accretion disk that generates immense amounts of energy. Some of this energy is expelled in the form of relativistic jets, which can travel across vast distances. This is a key feature of active galactic nuclei, AGN, a class of galaxies that includes many non-thermal radio galaxies. The high energy output from these galaxies allows them to be visible across great distances, making them some of the most luminous objects in the universe. One thing that distinguishes non-thermal radio galaxies from other types of galaxies is their strong, persistent radio emission. The radiation emitted by these galaxies is not thermal in nature, which is why they are called non-thermal. Unlike stars, which emit radiation as a result of their heat, thermal radiation, the radiation from non-thermal radio galaxies comes from particles that are moving at nearly the speed of light. These particles, mainly electrons, emit radiation when they interact with magnetic fields, causing them to spiral and accelerate. This synchrotron radiation is what gives these galaxies their distinctive radio signatures, and it can be detected using radio telescopes like the Very Large Array, VLA, and the Low Frequency Array, LOFAR. The fact that the radiation emitted by non-thermal radio galaxies is so intense and widespread means that it can be detected across vast cosmic distances. This ability to observe such galaxies in the far reaches of the universe provides valuable insight into the early history of the cosmos. Non-thermal radio galaxies are often among the most distant objects observed, which means they can offer a glimpse into the conditions of the universe at a time when it was still in its infancy. Some of the most distant and ancient galaxies are likely to have been radio galaxies, and studying these objects helps us piece together the cosmic timeline. In addition to the magnetic fields and jets, there is another fascinating aspect of non-thermal radio galaxies: the role of supermassive black holes in the overall structure and dynamics of the galaxy. These black holes, which can weigh billions of times the mass of the Sun, are the centers of the galaxies and the main engines behind the non-thermal radio emission. The gravitational pull of the black hole affects the motion of the surrounding stars and gas, shaping the galaxy's overall structure and determining how it evolves. The influence of black holes on their host galaxies is a topic of intense study, and it is believed that these objects play a critical role in regulating the growth and evolution of galaxies over time. There are also some striking similarities between non-thermal radio galaxies and other types of active galactic nuclei, such as Seyfert galaxies. Both types of galaxies exhibit high levels of radiation and are powered by supermassive black holes. However, while Seyfert galaxies typically have their energy output concentrated in the central region of the galaxy, non-thermal radio galaxies emit powerful jets that extend far beyond the galaxy's core. The existence of these jets is what sets non-thermal radio galaxies apart from other types of AGN and makes them so distinctive. In recent years, the use of advanced simulation techniques has allowed astronomers to model the behavior of non-thermal radio galaxies in greater detail. By simulating the interactions between the jets, the black hole, and the surrounding gas, scientists are gaining a deeper understanding of how these galaxies function. These simulations are also helping researchers understand how the jets form, how they interact with their environment, and how they evolve over time. By comparing these models with observations, astronomers can refine their theories and make predictions about the behavior of non-thermal radio galaxies under different conditions. Perhaps one of the most compelling reasons to study non-thermal radio galaxies is that they allow us to test some of the fundamental theories of physics. The extreme conditions found in these galaxies, such as the presence of supermassive black holes, relativistic particles, and intense magnetic fields, provide an opportunity to study the behavior of matter and energy in ways that are impossible to replicate on Earth. For example, the jets from these galaxies allow scientists to test our understanding of relativistic particle acceleration, the behavior of magnetic fields in extreme conditions, and the interaction between radiation and matter. These insights not only deepen our understanding of the universe but also have the potential to advance our knowledge of fundamental physics. As we continue to study non-thermal radio galaxies, it becomes increasingly clear that they are not just objects of curiosity but critical pieces of the cosmic puzzle. From their powerful jets to their influence on the surrounding gas and galaxies, these objects offer invaluable insights into the behavior of the universe at its most extreme scales. As our technology improves and our ability to observe distant galaxies grows, the mysteries of non-thermal radio galaxies will continue to unfold, offering new avenues of discovery that will shape our understanding of the cosmos for generations to come. The study of non-thermal radio galaxies does not just provide insights into the functioning of these distant objects, but it also has the potential to unlock broader mysteries of the universe itself. As scientists continue to observe and model these galaxies, they uncover clues that can help us answer some of the most fundamental questions about the universe. What drives the formation of galaxies? How do supermassive black holes influence their host galaxies and the surrounding cosmic environment? How do extreme environments like these help shape the evolution of the universe at large? Perhaps one of the most profound ways that non-thermal radio galaxies contribute to our understanding of the cosmos is through their role in cosmic feedback. This process, which involves the transfer of energy from the central supermassive black hole to the surrounding gas, has the potential to regulate the rate of star formation and even impact the overall structure of galaxies. When relativistic jets shoot out from the black hole, they can heat the gas and prevent it from cooling and collapsing to form new stars. Alternatively, they can provide the energy needed to trigger the formation of new stars in certain regions. This complex dance of energy transfer is one of the key mechanisms by which galaxies evolve, and non-thermal radio galaxies are at the heart of this process. The feedback from non-thermal radio galaxies is not just a small-scale phenomenon either. As we have already mentioned, the vast jets of particles and radiation emitted by these galaxies can extend over enormous distances, often stretching across millions of light-years. This means that non-thermal radio galaxies can influence the broader structure of galaxy clusters, potentially affecting the entire intergalactic medium. The high-energy radiation and particle jets from these galaxies play a crucial role in regulating the distribution of matter in the cosmos, which may help explain the large-scale structures of the universe, such as the cosmic web. Furthermore, the very nature of non-thermal radio galaxies, particularly their ability to emit powerful jets, is a window into understanding the underlying physics of high-energy processes in the universe. The jets themselves are not just particles flowing out from the black hole. They are also carriers of immense amounts of energy. These jets consist of highly energetic particles, such as electrons, which travel at nearly the speed of light. As they move through the magnetic field surrounding the galaxy, these particles spiral and accelerate, emitting synchrotron radiation in the form of radio waves. Understanding this process can teach us about the mechanisms of particle acceleration, the behavior of relativistic matter, and the interaction of matter with magnetic fields. In this way, non-thermal radio galaxies act as natural laboratories for studying the extreme conditions of the universe. The processes at play in these galaxies are far beyond what we can replicate on Earth, but by studying their radiation and particle dynamics, scientists can test theories of particle physics, magnetohydrodynamics, and general relativity. The fact that we can observe these galaxies across vast distances, sometimes billions of light years away, means that we are effectively looking back in time to the early stages of the universe. These observations provide an invaluable glimpse into how galaxies formed and evolved during the first few billion years after the Big Bang. One of the most exciting aspects of studying non-thermal radio galaxies is the way that they could help answer some of the most pressing questions about the formation of supermassive black holes. These black holes, which can be billions of times the mass of our Sun, are central to the formation of active galaxies, including non-thermal radio galaxies. It is believed that supermassive black holes form through a process of accretion and mergers, but the exact mechanisms behind this process remain a mystery. Non-thermal radio galaxies, with their powerful jets and intense energy emissions, could provide the key to understanding how black holes grow and evolve over time. By studying the interactions between the black holes and their surrounding environment, astronomers can test models of black hole formation and gain deeper insights into their role in galaxy evolution. Moreover, the jets produced by non-thermal radio galaxies are not simply a byproduct of black hole activity. They are central to the overall dynamics of the galaxy. These jets can carry energy away from the black hole, preventing the galaxy from becoming too quenched or starved of the gas needed to form new stars. In this sense, the jets are a form of cosmic feedback, regulating the rate of star formation and ensuring that the galaxy evolves in a balanced way. This feedback process is crucial for understanding the life cycle of galaxies and the role of black holes in shaping the overall structure of the universe. Non-thermal radio galaxies also present an intriguing opportunity to study the relationship between galaxies and their larger cosmic environments. These galaxies are often found in clusters, where the interaction between galaxies is common. When a non-thermal radio galaxy is located in a dense cluster, the interactions between its jets and the surrounding gas can have a significant impact on the evolution of the cluster as a whole. For example, the jets can heat the surrounding gas, preventing it from cooling and collapsing into new stars, thus regulating the star formation activity of the entire cluster. On a larger scale, these interactions can influence the structure of galaxy clusters and the way in which galaxies evolve over cosmic time. It is also important to note that not all non-thermal radio galaxies behave in the same way. There is a wide range of diversity among these galaxies, which suggests that their jets and their impact on the surrounding environment can vary greatly depending on their specific properties. Some non-thermal radio galaxies, for example, are relatively small and compact, while others can stretch across hundreds of thousands of light years, emitting powerful jets that reach far beyond their host galaxies. This variability is likely due to differences in the mass and spin of the central black hole, as well as the amount of material available for accretion. By studying the different types of non-thermal radio galaxies, astronomers can gain a better understanding of how black hole activity and galaxy evolution are linked. The diversity of non-thermal radio galaxies also points to the importance of understanding the role of magnetic fields in the universe. The jets emitted by these galaxies are often shaped and influenced by the magnetic fields surrounding the black hole. These fields can accelerate particles to near light speeds and guide them along the jet axis, leading to the formation of powerful, collimated jets. Magnetic fields also play a crucial role in the formation of the lobes, which are large regions of relativistic plasma that extend outward from the galaxy. By studying these magnetic fields and their interaction with the surrounding gas, scientists can gain insights into the behavior of matter and energy in extreme environments. The study of non-thermal radio galaxies also has practical implications for future astronomical research. With the advent of new radio telescopes, such as the Square Kilometre Array, SKA, scientists will be able to observe these galaxies in greater detail than ever before. The SKA, which will be the largest and most sensitive radio telescope ever built, will allow astronomers to study the radio emissions from distant galaxies with unprecedented precision. This will provide a wealth of new data that will help to answer key questions about the formation of galaxies, the behavior of black holes, and the evolution of the universe as a whole. Non-thermal radio galaxies are among the most fascinating and enigmatic objects in the universe. Their powerful jets, intense radiation, and complex interactions with their environment make them key players in the ongoing evolution of galaxies and galaxy clusters. As we continue to observe and study these objects, we uncover new insights into the fundamental forces that shape the cosmos. From their role in regulating star formation to their potential for unlocking the mysteries of black hole formation, non-thermal radio galaxies offer an unparalleled opportunity to explore the extremes of the universe. As our technology advances and our understanding deepens, these galaxies will continue to captivate astronomers and provide valuable clues to the workings of the universe on the grandest scales. As we continue to explore the fascinating world of non-thermal radio galaxies, the role they play in the broader cosmic ecosystem becomes even clearer. These galaxies, often overlooked in the past in favor of their more famous counterparts like Seyfert galaxies or quasars, have proven to be a crucial piece in the puzzle of how galaxies form, evolve, and interact with their surroundings. One of the most intriguing aspects of non-thermal radio galaxies is their relationship with the galactic environment. These galaxies are not isolated objects but are often part of larger cosmic structures like galaxy clusters. The high-energy jets and radiation emitted by non-thermal radio galaxies can have a profound impact on their immediate surroundings, heating up the intergalactic medium and influencing the behavior of nearby galaxies. The energy from the jets can prevent the accretion of gas into the galaxy, thereby regulating the star formation rate. In some cases, the jets even interact with other galaxies in the cluster, leading to what is known as radio mode feedback. This feedback mechanism can help regulate the size and growth of galaxy clusters, ensuring that they do not become too dense or overly star-forming. Furthermore, these interactions between non-thermal radio galaxies and their surrounding environments may help explain the phenomenon of radio halos. Radio halos are large regions of diffuse radio emission that surround galaxy clusters, and they are believed to be the result of interactions between the jets of non-thermal radio galaxies and the hot, diffuse gas that fills the cluster. These halos can stretch across vast distances, sometimes covering millions of light-years, and provide a fascinating glimpse into the long-term influence of non-thermal radio galaxies on their larger environments. The study of these halos is still in its early stages, but it is becoming increasingly clear that they play a significant role in the overall dynamics of galaxy clusters. On a more fundamental level, non-thermal radio galaxies provide a unique opportunity to probe the physical processes that govern the universe's most extreme environments. The jets emitted by these galaxies are composed of relativistic particles, traveling at nearly the speed of light, and the study of their behavior can reveal a great deal about the nature of high-energy physics. These jets interact with the magnetic fields in and around the galaxy, creating complex patterns of radiation and particle acceleration. Understanding how these interactions work could have far-reaching implications for our understanding of magnetism, particle physics, and even the very fabric of space-time. One particularly interesting aspect of these jets is their ability to produce synchrotron radiation. This occurs when charged particles are accelerated in magnetic fields, emitting electromagnetic radiation as they spiral around the field lines. In the case of non-thermal radio galaxies, the synchrotron radiation emitted by the particles in the jets is responsible for the powerful radio emissions we observe. The intensity and structure of this radiation provide clues about the density and strength of the magnetic fields, as well as the nature of the particle acceleration processes taking place in the galaxy's core. By studying the synchrotron radiation from these galaxies, astronomers can gain valuable insights into the behavior of magnetic fields and relativistic particles in the most extreme environments of the universe. Additionally, the study of non-thermal radio galaxies has implications for understanding the larger-scale structure of the universe. The jets emitted by these galaxies can interact with the surrounding intergalactic medium, influencing the distribution of matter in the universe. These interactions are thought to play a role in the formation of large-scale cosmic structures like galaxy clusters and superclusters. The powerful jets can inject energy into the surrounding gas, heating it and preventing it from cooling and collapsing into new stars. This process, known as heating feedback, is a key factor in regulating the growth and evolution of galaxies, and it may help explain the observed lack of new star formation in the cores of many massive galaxies. Interestingly, the influence of non-thermal radio galaxies extends far beyond the galaxies themselves. The jets emitted by these galaxies can travel across vast distances, impacting the surrounding environment and even neighboring galaxies. In some cases, these jets can extend well beyond the boundaries of the host galaxy, creating massive structures known as radio lobes. These lobes can span hundreds of thousands of light-years and are thought to be the result of the continuous outflow of particles from the galaxy's central supermassive black hole. The study of these lobes provides a glimpse into the power and scale of the energy produced by these galaxies, as well as the complex interplay between matter, energy, and magnetic fields in these extreme environments. The energy from these jets can also have a significant impact on the surrounding gas. The jets of relativistic particles interact with the hot gas in the galaxy's environment, creating shock waves and turbulence. These shock waves can heat the gas to incredibly high temperatures, preventing it from cooling and collapsing into new stars. In some cases, the jets can even create cavities in the surrounding gas, further reducing the amount of material available for star formation. This process, known as radio mode feedback, is a crucial mechanism for regulating the evolution of galaxies and galaxy clusters. By studying the feedback from non-thermal radio galaxies, scientists can gain insights into the broader processes that govern galaxy formation and evolution. In addition to their role in galaxy evolution, non-thermal radio galaxies are also important for understanding the history of the universe. These galaxies are often located at great distances from Earth, sometimes billions of light-years away. This means that when we observe them, we are essentially looking back in time, seeing them as they were in the distant past. By studying the properties of these galaxies, scientists can learn about the conditions that existed in the early universe and gain a better understanding of how galaxies formed and evolved over cosmic time. In particular, the study of non-thermal radio galaxies can help us understand the role of supermassive black holes in the early universe and their influence on the growth of galaxies. The jets emitted by these galaxies also provide a powerful tool for studying the universe's most distant and high redshift objects. When astronomers observe the jets of non-thermal radio galaxies, they are essentially looking at a snapshot of the universe at a particular point in time. By studying these jets, scientists can learn about the conditions that existed in the early universe and gain insights into the formation of galaxies and the growth of supermassive black holes. This information is crucial for understanding the broader evolution of the universe and the forces that shaped it. Non-thermal radio galaxies, in essence, serve as cosmic laboratories, offering a unique opportunity to study the fundamental forces that shape the universe. From their high-energy jets to their interactions with the surrounding gas, these galaxies provide a wealth of information about the workings of the cosmos. As our technology continues to advance, the study of these galaxies will only become more detailed, allowing us to unlock even more secrets about the universe's most extreme environments. By continuing to observe and analyze these fascinating objects, we are not only gaining insights into the lives of individual galaxies but also uncovering the broader processes that govern the evolution of the universe itself. The study of non-thermal radio galaxies is a key step in our ongoing quest to understand the fundamental forces that shape the cosmos. And as we look deeper into the heart of these mysterious objects, we are bound to uncover even more awe-inspiring discoveries. As we continue our journey into the intricacies of non-thermal radio galaxies, it is essential to delve deeper into the mechanisms that drive the powerful phenomena we observe. These galaxies, particularly the ones exhibiting active galactic nuclei, AGN, offer a unique window into the behavior of supermassive black holes and their surrounding accretion disks. The energy emitted by non-thermal radio galaxies is primarily linked to the activity at their core, where a supermassive black hole devours material and releases enormous amounts of energy in the form of relativistic jets. One of the key aspects that set non-thermal radio galaxies apart from other types of galaxies is the role of their supermassive black holes. These black holes are thought to be the primary engines behind the intense radio emissions observed in these galaxies. As matter spirals into the black hole, it heats up to extreme temperatures due to the immense gravitational forces. This heated material, along with the magnetic fields that permeate the region, creates a complex system of energy release. The supermassive black hole's immense gravitational pull causes the gas to rotate at high speeds, forming an accretion disk. This disk is a swirling mass of matter that eventually falls into the black hole, but not before it emits powerful jets along the poles of the black hole. These jets are what give non-thermal radio galaxies their characteristic features. The material that is ejected at relativistic speeds interacts with the surrounding gas, producing synchrotron radiation, radio waves created by charged particles moving through magnetic fields. The nature of this radiation, and its resulting radio emissions, are non-thermal in origin because they are not linked to the heat of the galaxy itself. Instead, they arise from these high-energy particles and their interactions with the intense magnetic fields around the black hole. Interestingly, the energy released by these jets can also play a critical role in regulating the growth and evolution of the galaxy. The powerful outflows can heat the surrounding intergalactic medium, preventing gas from cooling and condensing into new stars. This feedback mechanism is vital for understanding why some massive galaxies, despite having abundant gas, seem to stop forming stars after a certain point in their evolution. This process of feedback can help balance the growth of the galaxy, ensuring it does not become overly massive or overly star-forming, which could alter its balance in the cosmic ecosystem. The interaction of these jets with the surrounding medium can also produce structures that are visible to us from vast distances. The jets themselves, as they travel away from the galaxy's center, often expand and spread out, creating vast lobes of radio emission on either side of the galaxy. These lobes are known as radio lobes, and they can stretch for millions of light years, giving the galaxy a characteristic double-lobed appearance. The size of these lobes is a reflection of the energy and power behind the jets, and studying their shape and structure provides valuable insight into the mechanics of jet formation and propagation. The dynamics of these lobes are also influenced by the surrounding gas. As the jets move through the intergalactic medium, they can push against the gas, creating shock waves that heat and stir the surrounding material. These shock waves are thought to play a crucial role in the regulation of star formation within the galaxy. By preventing the gas from cooling and condensing, they effectively quench star formation in the galaxy's core. The energy injected into the intergalactic medium by these jets also helps to maintain the overall temperature of the surrounding gas, which can prevent it from collapsing into dense clouds that could potentially form new stars. One of the most fascinating aspects of studying non-thermal radio galaxies is the role they play in the larger structure of the universe. These galaxies are often located in galaxy clusters, which are vast cosmic structures that contain hundreds or even thousands of individual galaxies. The energy released by the jets of non-thermal radio galaxies can have a significant impact on the cluster as a whole. For instance, the jets can inject energy into the hot gas that fills the cluster, preventing it from cooling and collapsing into new stars. This process of heating the cluster gas is crucial for the overall stability of the cluster, and it helps to maintain the balance between the galaxies and their environment. In fact, some of the most massive galaxy clusters in the universe are known to harbor large numbers of non-thermal radio galaxies. These clusters, which are often referred to as radio clusters, contain an abundance of active galaxies that produce powerful jets. The energy from these jets can shape the overall dynamics of the cluster, helping to regulate its growth and evolution. In some cases, the jets can even lead to the formation of massive radio halos, huge regions of diffuse radio emission that stretch across the entire cluster. These halos are believed to be the result of the interaction between the jets of the galaxies and the hot gas in the cluster. The study of these radio halos is a rapidly developing field, and it provides a unique perspective on the impact of non-thermal radio galaxies on the larger-scale structure of the universe. On a cosmological scale, non-thermal radio galaxies offer a unique tool for studying the formation and evolution of galaxy clusters and superclusters. By studying the jets and lobes of these galaxies, astronomers can gain valuable insights into the processes that govern the behavior of matter on the largest scales. The jets from these galaxies can influence the distribution of gas and matter within a cluster, and they can even shape the large-scale structure of the universe itself. In this way, the The study of non-thermal radio galaxies is not just important for understanding individual galaxies but also for understanding the broader processes that govern the formation and evolution of the cosmos. As we push the boundaries of our understanding of these remarkable objects, we are constantly uncovering new and unexpected discoveries. One of the key challenges in studying non-thermal radio galaxies is understanding the physical processes that occur within the jets themselves. These jets, which are composed of relativistic particles moving at nearly the speed of light, are highly complex systems that are influenced by a variety of factors, including magnetic fields, gas densities, and the properties of the central black hole. By studying the behavior of the jets, astronomers hope to gain a deeper understanding of the fundamental forces that govern the universe. The study of non-thermal radio galaxies also has implications for our broader understanding of high-energy astrophysics. The relativistic particles in the jets of these galaxies provide a natural laboratory for studying the behavior of particles in extreme environments. The acceleration of these particles to nearly the speed of light, along with the intense magnetic fields that govern their movement, offers valuable insights into the physics of particle acceleration and magnetohydrodynamics. These insights could help us better understand a range of phenomena, from the behavior of particles in high-energy astrophysical systems to the fundamental nature of magnetism itself. In the coming years, the study of non-thermal radio galaxies will likely continue to play a crucial role in shaping our understanding of the universe. With the advent of new observational techniques, such as advanced radio telescopes and high-resolution imaging, we are poised to uncover even more details about these enigmatic objects. As we look deeper into the jets, lobes, and surrounding environments of non-thermal radio galaxies, we will gain a clearer picture of the forces that govern the evolution of galaxies and the broader structure of the cosmos. As we continue to explore the fascinating world of non-thermal radio galaxies, it is important to recognize that these objects are not only significant in the study of galaxy formation but also offer a critical window into the nature of cosmic evolution itself. The sheer power and scale of the phenomena associated with these galaxies provide us with clues about the life cycle of galaxies, the dynamics of supermassive black holes, and the role of energy outflows in the cosmic ecosystem. The study of non-thermal radio galaxies is intrinsically linked to the broader concept of active galactic nuclei, AGN. These AGN are the energetic and highly luminous centers of galaxies, driven by supermassive black holes. When matter falls into these black holes, it spirals into the accretion disk, where the material heats up to incredibly high temperatures due to the immense gravitational forces. This results in the release of vast amounts of energy in the form of electromagnetic radiation, including radio waves, X-rays, and gamma rays. The energy emitted by the central black hole is often so powerful that it can outshine the rest of the galaxy combined. What sets non-thermal radio galaxies apart is the nature of the radiation they emit. Unlike galaxies where the primary energy source is thermal radiation, non-thermal radio galaxies are dominated by the emission of synchrotron radiation, which originates from the acceleration of charged particles through magnetic fields. This distinction is critical in understanding the underlying processes that govern these galaxies. The magnetic fields that permeate these galaxies, often extending far beyond the galaxy's core, play a crucial role in shaping the behavior of the radio-emitting jets. One of the most interesting aspects of non-thermal radio galaxies is the way in which their radio jets are aligned. In many cases, the jets are aligned with the central black hole's spin axis, which is the result of the black hole's rotational dynamics. This alignment indicates a highly ordered structure within the galaxy, where the energy output from the black hole is funneled along the jets in a specific direction. The alignment of these jets can be observed across vast distances, and the study of this alignment provides important clues about the mechanics of supermassive black holes and the relationship between the black hole and its surrounding accretion disk. The study of non-thermal radio galaxies is not limited to simply understanding individual objects in isolation. These galaxies are often found in galaxy clusters, which are massive gravitationally bound systems that can contain hundreds or even thousands of galaxies. Within these clusters, non-thermal radio galaxies can have a profound impact on the surrounding environment. The jets and lobes of these galaxies can inject significant amounts of energy into the intergalactic medium, heating the gas that fills the cluster. This energy injection can prevent the gas from cooling and condensing into new stars, which has important implications for the growth and evolution of the galaxy cluster. In some cases, the energy from these jets is so powerful that it can alter the large-scale structure of the cluster itself. The energy output from the jets can drive shock waves through the hot gas in the cluster, leading to a process known as feedback. This feedback mechanism plays a key role in regulating the formation of new stars within the cluster. By preventing the gas from cooling and collapsing, the jets help to maintain the stability of the cluster and prevent it from undergoing rapid star formation. This feedback process also helps to maintain the overall balance of the cluster, ensuring that it does not become overly dominated by a single galaxy or group of galaxies. One of the key tools used to study non-thermal radio galaxies is the observation of their radio emissions. Radio telescopes, such as the Very Large Array, VLA, in New Mexico and the Atacama Large Millimeter/Submillimeter Array, ALMA, in Chile, have allowed astronomers to map the radio emissions of these galaxies with incredible detail. By studying the distribution and structure of the radio lobes and jets, scientists can gain a better understanding of the underlying physical processes at work within these galaxies. One of the most striking features of non-thermal radio galaxies is the vast size of their radio lobes. These lobes, which can extend for millions of light-years, are the result of the jet's interactions with the surrounding medium. As the jets propagate through the intergalactic gas, they compress the gas and create shock waves that lead to the formation of these massive lobes. The size of these lobes is directly related to the energy output of the central black hole. More powerful black holes, which release larger amounts of energy through their jets, produce larger and more extended radio lobes. The study of these lobes is crucial for understanding the relationship between the central black hole and its environment, as well as the mechanisms that drive the formation of these lobes. The interaction between the jets and the surrounding medium also leads to the production of synchrotron radiation, which is responsible for the characteristic radio emission from non-thermal radio galaxies. This radiation is produced when charged particles, such as electrons, move through magnetic fields at relativistic speeds. The resulting synchrotron radiation is not thermal, meaning it does not come from the heat of the galaxy itself, but instead originates from the high-energy particles accelerated by the magnetic fields in the jets. This process is highly efficient, meaning that the radio emissions from non-thermal radio galaxies can be incredibly powerful. In addition to radio emission, non-thermal radio galaxies also emit high-energy radiation in the form of X-rays and gamma rays. This high-energy radiation is often produced by the same processes that generate the radio waves, but at much higher frequencies. The study of this high-energy emission is critical for understanding the extreme conditions within the central regions of these galaxies. High-energy radiation is typically produced when charged particles are accelerated to near-light speeds, either through the influence of the black hole's gravity or through magnetic field interactions. The ability to detect and study these high-energy emissions gives astronomers a unique insight into the extreme environments surrounding supermassive black holes. The role of magnetic fields in non-thermal radio galaxies is another key area of study. Magnetic fields are thought to play a central role in the formation of the jets and the propagation of the radio emissions. These fields are often present in the accretion disk surrounding the black hole, where they are thought to help channel the energy from the accreting material into the relativistic jets. Once the jets are launched, the magnetic fields continue to influence their behavior, helping to accelerate the particles within the jets and maintain the structure of the radio lobes. The study of magnetic fields in non-thermal radio galaxies is a rapidly evolving field, and new observations are continually shedding light on the complex interactions between magnetic fields and the high-energy particles that populate these galaxies. The impact of non-thermal radio galaxies extends beyond their own galaxies and clusters. These objects are often found in regions of space that are rich in galactic activity, and their powerful jets can influence the evolution of other galaxies within their vicinity. For example, the jets from one galaxy can interact with the gas and dust in neighboring galaxies, leading to the redistribution of matter and energy. In some cases, these interactions can lead to the formation of new stars or even trigger the growth of new black holes. The feedback mechanisms involved in these interactions play a crucial role in the overall evolution of the galaxy cluster and can help to shape the large-scale structure of the universe itself. As we continue to observe and study non-thermal radio galaxies, it is clear that they are key players in the complex dynamics of the universe. Their ability to inject vast amounts of energy into the surrounding medium, along with their impact on galaxy formation and evolution, makes them essential objects for understanding the cosmos. Through advances in observational techniques and the continued study of these galaxies, we are sure to uncover even more about the fundamental processes that drive the evolution of galaxies and the larger-scale structure of the universe. Continuing with the exploration of non-thermal radio galaxies, it's important to understand how their study is not just an academic pursuit, but a key to unlocking some of the most profound mysteries of the cosmos. Their unique characteristics challenge our understanding of astrophysics, the mechanics of black holes, and the overall evolution of galaxies. By studying the jets, magnetic fields, and the feedback mechanisms at play in these galaxies, we are not only learning about the galaxies themselves but also about the fundamental processes that govern the universe on the largest scales. One of the most intriguing aspects of non-thermal radio galaxies is the phenomenon of radio galaxy morphologies. The shapes of these galaxies, particularly the radio lobes and jets, can vary dramatically depending on the conditions within the galaxy and the surrounding environment. In some cases, these radio galaxies exhibit wide-angle tails in their radio lobes, which are long, curved structures that extend far from the central galaxy. These tails are the result of the interactions between the relativistic jets and the surrounding intergalactic medium. The exact mechanisms behind these wide-angle tails are still not fully understood, but they provide critical insight into the interactions between the galaxy and the larger cosmic environment. Another fascinating feature of non-thermal radio galaxies is the presence of hotspots at the ends of the radio lobes. These hotspots are regions of intense emission that are believed to be caused by the interaction between the relativistic jets and the intergalactic medium. When the jets collide with the surrounding gas, the shock waves created by the impact can accelerate particles to extremely high energies, resulting in the production of intense synchrotron radiation. The study of these hotspots can reveal important details about the density and composition of the intergalactic medium, as well as the energy distribution within the jets. The role of supermassive black holes in non-thermal radio galaxies cannot be overstated. These black holes, which sit at the centers of most galaxies, are the engines that power the radio jets. The process by which matter falls into a black hole, known as accretion, is one of the most energetic phenomena in the universe. As material is pulled toward the black hole, it forms a hot, swirling disk of gas and dust known as the accretion disk. The material in this disk is heated to incredibly high temperatures, causing it to emit a broad spectrum of radiation. However, it is the powerful magnetic fields in the accretion disk and around the black hole that are primarily responsible for launching the jets and directing them outward at nearly the speed of light. The size and energy output of the jets are directly related to the mass and spin of the black hole. More massive and rapidly rotating black holes tend to produce larger, more energetic jets. In fact, the spin of the black hole plays a key role in determining the structure and behavior of the jets. This relationship between black hole spin and jet formation is a subject of intense study, as it could provide valuable insight into the fundamental mechanics of black hole accretion and the nature of the energy release in non-thermal radio galaxies. Another key aspect of non-thermal radio galaxies is the role of cooling processes within the intergalactic medium. The energetic jets emitted by these galaxies inject large amounts of energy into the surrounding gas, which can cause it to heat up and prevent it from cooling. This process is known as heating, and has important implications for the formation of stars within galaxy clusters. The heating effect of the jets can suppress star formation by preventing the gas from cooling and collapsing into dense regions where new stars could form. This phenomenon, known as feedback, plays a crucial role in regulating the growth and evolution of galaxies and clusters, helping to maintain a balance between the energy input from the black holes and the ability of the gas to cool and condense into stars. The study of cooling and feedback processes in non-thermal radio galaxies is made possible by the use of various astronomical instruments that can observe different wavelengths of electromagnetic radiation. For example, X-ray telescopes like the Chandra X-ray Observatory provide detailed images of the hot gas in galaxy clusters, while radio telescopes like the VLA allow astronomers to map the radio emissions from the jets and lobes of these galaxies. By combining observations from multiple wavelengths, scientists can gain a comprehensive understanding of the interactions between the jets, the surrounding gas, and the larger galaxy cluster. One of the challenges in studying non-thermal radio galaxies is the fact that their jets and lobes are often located in the farthest reaches of the universe, making them difficult to observe. The immense distances involved mean that we are often looking at these galaxies as they were billions of years ago, when they were still in the early stages of their evolution. As a result, the data we collect from these galaxies can only offer a snapshot of their behavior at a particular moment in time. Nevertheless, the study of these galaxies provides valuable insights into the processes that shape the universe, and the information we gain from these distant objects can be applied to our understanding of galaxies closer to home. Non-thermal radio galaxies are also valuable because they provide a testing ground for many of the theories in astrophysics. For example, the study of the jets in these galaxies helps to test models of high-energy particle acceleration, magnetic field generation, and the dynamics of relativistic flows. These models are not only applicable to radio galaxies but also to other cosmic phenomena, such as gamma-ray bursts and the activity observed in quasars. By studying the jets and lobes of non-thermal radio galaxies, we can test these theories in a real-world context, helping to refine our understanding of fundamental astrophysical processes. Interestingly, non-thermal radio galaxies have also been linked to other high-energy phenomena, such as the detection of high-energy cosmic rays. Cosmic rays are charged particles that travel at nearly the speed of light and are often produced by the most energetic events in the universe. The study of these cosmic rays is still in its early stages, but there is growing evidence that non-thermal radio galaxies may be a significant source of these high-energy particles. The jets from these galaxies are capable of accelerating particles to relativistic speeds, and some of these particles may eventually escape from the galaxy and travel through the intergalactic medium, contributing to the overall population of cosmic rays. In addition to cosmic rays, non-thermal radio galaxies are also thought to play a role in the production of other exotic particles, such as neutrinos. Neutrinos are nearly massless, electrically neutral particles that rarely interact with matter, making them incredibly difficult to detect. However, some researchers believe that non-thermal radio galaxies could be a source of high-energy neutrinos, particularly those that are associated with the jets. Neutrinos are produced when high-energy particles interact with the surrounding gas, and the study of these elusive particles could provide further insight into the extreme environments of non-thermal radio galaxies. The link between non-thermal radio galaxies and the larger cosmic structure is another aspect that makes these objects so intriguing. The energy released by the jets of these galaxies can have a profound impact on the intergalactic medium, the vast expanse of gas and dust that fills the space between galaxies. This energy can prevent the gas from cooling, which in turn affects the formation of new stars and galaxies. The feedback from non-thermal radio galaxies plays a crucial role in shaping the evolution of the universe, as it helps to regulate the growth of galaxies and the formation of cosmic structures. In this way, these galaxies are not just isolated objects but active participants in the cosmic ecosystem, helping to shape the future of the universe itself. Continuing the discussion on non-thermal radio galaxies, the immense influence these galaxies have on the surrounding environment is crucial for understanding the broader dynamics of the universe. The powerful jets emitted by non-thermal radio galaxies can interact with the hot, ionized gas in galaxy clusters, often creating complex structures that extend across vast distances. These interactions can produce phenomena such as shock waves and turbulence, which can further affect the evolution of the galaxy cluster as a whole. In particular, the feedback mechanism between the radio jets and the surrounding medium can lead to what is known as heating in galaxy clusters. This heating is important because it prevents the gas from cooling too quickly, a process that could otherwise lead to an excessive amount of star formation. In clusters where the heating is more pronounced, star formation rates are often much lower than in other regions of the universe, and this plays a significant role in the formation of large elliptical galaxies. The energy injected by non-thermal radio galaxies can thus regulate the star formation history of galaxies and clusters, influencing the overall cosmic evolution. Additionally, the phenomenon of radio mode feedback is an important consideration in the study of non-thermal radio galaxies. This type of feedback refers to the process where the central supermassive black hole's activity, particularly the launching of relativistic jets, acts to regulate the cooling of the surrounding gas. In this feedback loop, the energy from the radio jets suppresses the cooling of the gas, thus preventing the collapse of the gas into dense regions where new stars could form. This process is thought to play a major role in the formation and growth of large elliptical galaxies and in maintaining the balance of matter in galaxy clusters. The study of non-thermal radio galaxies also reveals important information about the state of the intergalactic medium, IGM. The IGM is the diffuse gas that exists between galaxies, and its properties are not fully understood. In some cases, non-thermal radio galaxies can provide valuable insights into the density and composition of this medium. The jets from these galaxies often interact with the IGM, producing observable phenomena such as shock waves and particle acceleration. The presence of these shock waves can help scientists understand the temperature, density, and composition of the gas in the IGM, providing a more complete picture of the universe's structure. One of the major challenges in studying non-thermal radio galaxies is the enormous distances involved. These galaxies are often located billions of light-years away, making direct observations incredibly difficult. Despite these challenges, astronomers have developed sophisticated techniques to study these galaxies using radio telescopes and other instruments. For example, the Very Large Array, VLA, is a powerful radio telescope that has been instrumental in the study of non-thermal radio galaxies. By using the VLA to observe the radio emissions from these galaxies, scientists can create detailed maps of the jets and lobes, providing valuable information about their structure and behavior. In addition to radio telescopes, astronomers also use other instruments, such as X-ray telescopes, to study the hot gas that surrounds non-thermal radio galaxies. X-ray observations allow scientists to map the temperature and density of the gas, which can help them understand the interaction between the jets and the intergalactic medium. By combining data from multiple wavelengths of light, scientists can create a more complete picture of the processes occurring within these galaxies. The role of magnetic fields in non-thermal radio galaxies is another critical area of research. These magnetic fields are responsible for the acceleration of particles to relativistic speeds, which is essential for the production of synchrotron radiation. The magnetic fields in non-thermal radio galaxies are incredibly strong and can influence the structure and behavior of the jets. In some cases, the magnetic fields can become twisted and chaotic, leading to the formation of complex jet structures. The study of these magnetic fields can reveal important information about the processes that govern the formation and behavior of jets, as well as the overall dynamics of the galaxy. A key aspect of the study of non-thermal radio galaxies is the relationship between the central supermassive black hole and the surrounding galaxy. The jets produced by the black hole can have a significant impact on the galaxy, affecting both its star formation rate and its overall evolution. In some cases, the feedback from the jets can suppress star formation, leading to the formation of a dead galaxy, where little to no new stars are formed. In other cases, the jets can help to trigger star formation by compressing the gas in the surrounding galaxy. Understanding this relationship is crucial for understanding how galaxies evolve over time and how they interact with their environments. Non-thermal radio galaxies also provide important clues about the nature of active galactic nuclei, AGN. An AGN is a region at the center of a galaxy that is extremely bright due to the presence of a supermassive black hole. The energy released by the accretion of matter onto the black hole powers the AGN, and in some cases, this energy is channeled into the formation of relativistic jets. These jets are what make non-thermal radio galaxies so distinct from other types of galaxies. The study of AGNs in non-thermal radio galaxies is crucial for understanding the role of supermassive black holes in galaxy formation and evolution. Interestingly, the study of non-thermal radio galaxies has also led to the discovery of rare and unusual phenomena, such as relic and ghost radio galaxies. These are objects that no longer have active jets but still emit faint radio waves, often long after the jets have stopped. These relics are thought to be the remnants of older radio galaxies, and their study can provide valuable insights into the life cycle of jets and the overall evolution of non-thermal radio galaxies. In some cases, relic radio galaxies have been found in galaxy clusters, where they can serve as a marker of the past activity of the central supermassive black hole. Another fascinating aspect of non-thermal radio galaxies is their role in the study of cosmic evolution. By examining these galaxies, scientists can gain a deeper understanding of how galaxies and galaxy clusters evolve over time. The feedback mechanisms that are observed in non-thermal radio galaxies are thought to play a crucial role in shaping the large-scale structure of the universe. For example, the heating and suppression of star formation that occurs in these galaxies can help prevent the overgrowth of galaxies and clusters, maintaining a balance between the creation of new stars and the regulation of existing ones. This balance is essential for the overall evolution of the universe, and understanding it is key to unlocking the mysteries of cosmic history. The study of non-thermal radio galaxies has also provided important insights into the nature of dark matter. Dark matter is a mysterious substance that makes up a significant portion of the universe's mass, yet it cannot be directly observed. Scientists have hypothesized that dark matter exists based on its gravitational effects on visible matter, and the study of non-thermal radio galaxies can help test these theories. The way that jets from these galaxies interact with the surrounding medium can provide clues about the distribution of dark matter in galaxy clusters. Additionally, the study of the large-scale structure of the universe, which is shaped in part by dark matter, is enhanced by understanding the role of non-thermal radio galaxies. As our technology continues to improve, the study of non-thermal radio galaxies will only become more refined. With the advent of next-generation radio telescopes, such as the Square Kilometre Array, SKA, scientists will be able to observe these galaxies in even greater detail, enabling new discoveries and insights. The SKA, in particular, is expected to revolutionize our understanding of non-thermal radio galaxies by providing an unprecedented view of the universe's most energetic objects. The SKA will allow astronomers to observe these galaxies with greater sensitivity and resolution, making it possible to study the intricate structures of the jets and lobes in greater detail than ever before. The study of non-thermal radio galaxies is a critical area of research that offers a wealth of insights into the nature of the universe. These galaxies are not only fascinating objects in their own right, but they also serve as valuable tools for understanding a wide range of astrophysical phenomena. From the powerful jets and magnetic fields that shape their structure to the feedback mechanisms that regulate the growth of galaxies and clusters, non-thermal radio galaxies provide a unique window into the complex processes that govern the cosmos. As our observational capabilities continue to improve, the mysteries of these galaxies will no doubt become clearer, offering new opportunities for discovery and a deeper understanding of the universe. The future of non-thermal radio galaxy research is closely tied to advances in our observational capabilities and theoretical understanding. As more powerful telescopes come online, particularly those focused on radio wavelengths, scientists will be able to probe these galaxies in even greater detail. One of the most exciting prospects is the ability to explore how the most distant non-thermal radio galaxies evolved over billions of years, offering a glimpse into the universe's early stages. The role of non-thermal radio galaxies in our understanding of cosmic inflation, the rapid expansion of the universe just after the Big Bang, cannot be overstated. The jets emitted by these galaxies, with their high energy and vast reach, provide a unique lens through which we can study the matter and energy that filled the universe long ago. Because non-thermal radio galaxies are typically located at vast distances, observing them effectively means looking back in time, at a universe that was in its infancy. This allows researchers to understand better how energy was distributed and how galaxies began to form in the early stages of the universe. Even within the context of current scientific knowledge, these galaxies still present numerous mysteries. One of the primary challenges is the lack of a clear understanding of the exact mechanisms that accelerate particles to relativistic speeds, which are necessary for the emission of synchrotron radiation in the first place. While we have a basic grasp of the importance of magnetic fields in this process, there is still much to learn about the intricate details of particle acceleration and jet formation. Some theories propose that the magnetic fields in non-thermal radio galaxies can be so intense that they effectively trap high-energy particles, creating a sort of cosmic conveyor belt that powers the jets and lobes of these galaxies. These ideas, while fascinating, remain speculative and are in need of further testing and observation. Another key question that continues to challenge scientists is why non-thermal radio galaxies often appear to undergo cycles of activity and dormancy. The central supermassive black holes in these galaxies are known to go through phases of high and low activity, yet the exact mechanisms that govern these cycles remain unclear. It's possible that the surrounding gas, the availability of fuel for the black hole, or interactions with nearby galaxies could all influence the black hole's activity. This dynamic process is known as AGN feedback, and the cycling of jet activity is an important area of study. Understanding these cycles can provide insight into how galaxies evolve over time, and how they maintain their balance between accreting mass and emitting powerful jets. The study of non-thermal radio galaxies also has applications in other branches of physics, particularly in understanding relativistic fluids and magnetohydrodynamics, MHD. The incredibly fast-moving plasma jets seen in these galaxies are excellent laboratories for studying the properties of relativistic fluids, which are fluids that move at speeds close to the speed of light. By studying these jets, scientists can gain a better understanding of how such fluids behave under extreme conditions, which could have applications beyond astrophysics, such as in the fields of fusion energy and plasma physics. The discovery of ghost and relic radio galaxies has further expanded our understanding of the life cycle of these objects. These remnants of once active galaxies offer valuable information about the history of non-thermal radio galaxies and the mechanisms that drive their activity. The discovery of ghost radio galaxies, in particular, has raised fascinating questions about the time scales involved in jet formation and activity. It is clear that the process of launching and sustaining jets is not instantaneous. Instead, it occurs over millions of years. These long-lived remnants provide a unique opportunity to study the fading echoes of once powerful cosmic phenomena, offering a snapshot of the universe's evolution over vast stretches of time. Beyond the study of individual galaxies, non-thermal radio galaxies are also crucial for understanding the large-scale structure of the universe. The interaction between the jets of these galaxies and the intergalactic medium, IGM, can have far-reaching consequences for the distribution of matter in the universe. As these jets heat and disturb the surrounding gas, they can influence the growth and distribution of galaxy clusters, potentially affecting the formation of large-scale cosmic structures. By studying non-thermal radio galaxies and their impact on the IGM, astronomers can refine their models of how the universe evolved and how it continues to evolve today. One interesting aspect of non-thermal radio galaxies is the diversity of their structures. Some galaxies are known for having large, well-defined radio lobes that extend for hundreds of thousands of light-years. These lobes are the result of the energy being pushed outward by the jets, forming vast regions of diffuse gas and magnetic fields. In contrast, other galaxies may have more compact radio lobes or no visible lobes at all, depending on the orientation of their jets and the surrounding environment. The diversity in structure suggests that non-thermal radio galaxies can take on many different forms, depending on factors such as the environment in which they are located, the age of the galaxy, and the properties of the central supermassive black hole. As we look to the future, the study of non-thermal radio galaxies will undoubtedly continue to evolve, with new techniques and methodologies coming into play. One area of particular interest is the potential for combining data from multiple wavelengths of light, radio, optical, infrared, X-ray, and gamma-ray, to create a multidimensional view of these galaxies. By cross-referencing observations from these different wavelengths, scientists can gain a more complete picture of the physical processes that govern non-thermal radio galaxies. This multi-wavelength approach has already proven successful in the study of many other astrophysical phenomena and is likely to reveal even more about the behavior of these fascinating objects. A major milestone in the field of radio astronomy is the development of the Square Kilometre Array, SKA, a project that promises to revolutionize our understanding of non-thermal radio galaxies. The SKA will be the largest radio telescope ever built, and its immense sensitivity and resolution will allow for unprecedented observations of distant galaxies. With its ability to detect faint radio emissions from the earliest stages of galaxy formation, the SKA is poised to provide crucial data on the evolution of non-thermal radio galaxies and their role in the larger cosmic story. By probing the most distant regions of the universe, the SKA will help answer fundamental questions about the formation and evolution of galaxies, the behavior of supermassive black holes, and the nature of the intergalactic medium. Beyond the technical advancements that the SKA promises, the study of non-thermal radio galaxies will also contribute to some of the most profound questions in astrophysics. For example, the observation of non-thermal radio galaxies in the early universe may provide key insights into the processes that govern galaxy formation and evolution. By studying these galaxies, scientists can refine their models of how galaxies first came together and how they evolved over time. Furthermore, the feedback processes seen in non-thermal radio galaxies may offer a deeper understanding of how energy is distributed throughout the universe, shedding light on the nature of dark energy and the overall fate of the cosmos. In the coming years, the study of non-thermal radio galaxies will continue to be a vibrant and rapidly evolving field of research. As our tools for observing the universe become more advanced and as our theoretical models continue to improve, the mystery surrounding these fascinating objects will begin to unravel. The insights gained from studying non-thermal radio galaxies have the potential to reshape our understanding of the universe, from the formation of galaxies to the evolution of large-scale cosmic structures. The energy, the jets, and the complex interactions that these galaxies exhibit are more than just curiosities. They are keys to unlocking the deepest secrets of the cosmos. As we continue to explore the fascinating world of non-thermal radio galaxies, it's important to take a moment to reflect on their significance in the broader context of cosmology and astrophysics. These galaxies, with their powerful jets and mysterious emissions, are more than just distant objects in the universe. They provide us with invaluable insights into some of the most fundamental processes that govern the universe, from the behavior of matter under extreme conditions to the complex interactions between galaxies and the intergalactic medium. As we dive deeper into the study of these galaxies, we are not only uncovering the mechanics of these cosmic phenomena but also answering some of the most pressing questions about the origins and evolution of the universe itself. One of the aspects of non-thermal radio galaxies that continue to captivate researchers is the behavior of the supermassive black holes at their cores. These black holes are often the engines driving the energetic jets and lobes that make these galaxies so distinct. But what exactly powers these jets, and how do they remain active over such long periods of time? The exact mechanism of jet formation is still an area of active research, but we know that it involves complex interactions between the accretion disk, the magnetic field surrounding the black hole, and the infall of gas and other matter. The accretion disk is formed when matter is drawn toward the black hole, forming a hot, rotating disk of gas and dust. Magnetic fields in this region are thought to play a crucial role in channeling the energy of the accretion disk into powerful jets that extend far beyond the galaxy. The process of accretion and jet formation is not fully understood, and there is ongoing debate among scientists as to the specifics of how it works. One theory suggests that the magnetic fields surrounding the black hole are so strong that they can channel particles from the accretion disk into relativistic jets that travel at near the speed of light. These jets are composed of high-energy particles such as electrons, protons, and even heavier ions, all of which emit radiation as they move through the magnetic fields. This radiation can take many forms, including synchrotron radiation, which is responsible for the radio emissions we detect from these galaxies. The challenge for researchers is understanding the details of this process and how it leads to the observed emission of non-thermal radiation. The study of the magnetic fields in non-thermal radio galaxies is another key area of investigation. magnetic fields play a fundamental role in shaping the structure of the jets and lobes seen in these galaxies. In fact, some scientists propose that the magnetic fields are not only responsible for accelerating the particles but also for shaping the jets themselves. The exact configuration of these magnetic fields, whether they are aligned or tangled, can have a significant impact on the structure of the radio lobes and the overall morphology of the galaxy. Researchers are using advanced techniques, including polarization measurements, to map out the structure of these magnetic fields in greater detail, with the aim of uncovering the underlying physics behind their behavior. In addition to the study of magnetic fields, the interactions between the jets and the surrounding environment are also of great interest. As the jets travel outward from the black hole, they encounter the intergalactic medium, IgM, which is a diffuse and tenuous gas that exists between galaxies. The jets can have a profound impact on the IgM, heating it up and disturbing its structure. This interaction is thought to play a crucial role in regulating the growth of galaxy clusters, as the energy from the jets can influence the distribution of gas and prevent the cooling of the IgM. In this way, the jets from non-thermal radio galaxies are not just isolated phenomena, they are key players in the broader dynamics of the universe. The role of non-thermal radio galaxies in galaxy cluster formation is another area that has garnered significant attention. The feedback processes associated with the jets and their interaction with the IgM can affect the evolution of galaxy clusters, which are the largest gravitationally bound structures in the universe. When a non-thermal radio galaxy emits a powerful jet, it injects energy into the surrounding gas, preventing it from cooling and condensing to form new stars. This process, known as AGN feedback, is thought to regulate the growth of galaxies and clusters by limiting the amount of gas available for star formation. Understanding how these feedback mechanisms work is essential for developing a more complete picture of galaxy evolution and the large-scale structure of the universe. A particularly intriguing aspect of non-thermal radio galaxies is their potential to provide insights into dark matter and dark energy. While these elusive components of the universe remain largely mysterious, the study of non-thermal radio galaxies could offer clues about their nature and behavior. For example, the way in which jets interact with the surrounding medium could help us understand the distribution of dark matter in galaxy clusters. Dark matter, which is thought to make up a significant portion of the universe's mass, has a gravitational influence on visible matter, but it does not emit or interact with light in the same way that normal matter does. By studying the way in which non-thermal radio galaxies influence their surroundings, scientists may be able to learn more about the distribution and properties of dark matter. Similarly, the study of non-thermal radio galaxies could also provide clues about the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. While the connection between non-thermal radio galaxies and dark energy is not immediately obvious, the way in which these galaxies impact the expansion of the universe could reveal something about the nature of dark energy. For example, by studying the distribution of galaxies with powerful jets and comparing them to other types of galaxies, researchers can probe the influence of dark energy on large-scale cosmic structures. This could help us refine our models of the universe's expansion and provide insights into the underlying causes of cosmic acceleration. The future of non-thermal radio galaxy research will likely continue to be shaped by advancements in observational technology. In particular, the next generation of radio telescopes will play a pivotal role in expanding our understanding of these galaxies. The Square Kilometre Array, SKA, a massive radio telescope currently under construction, promises to revolutionize our ability to study non-thermal radio galaxies. The SKA will be able to observe the universe in unprecedented detail, allowing researchers to explore even the most distant and faint galaxies. This could lead to a better understanding of the mechanisms that drive the formation of jets, as well as the ways in which these galaxies interact with their environments. In addition to the SKA, other upcoming facilities, such as the James Webb Space Telescope and the next generation of ground-based telescopes, will further enhance our observational capabilities. These instruments, with their ability to observe in multiple wavelengths of light, will provide a more comprehensive view of non-thermal radio galaxies. By combining data from radio, optical, and infrared telescopes, scientists will be able to study these galaxies in greater detail, gaining new insights into their structure, evolution, and role in the cosmos. As we look to the future, the study of non-thermal radio galaxies will continue to push the boundaries of our understanding of the universe. These galaxies are not just distant objects in the sky, they are key players in the ongoing story of the cosmos. Through continued research, we will uncover new layers of knowledge about the fundamental processes that govern the universe, from the behavior of supermassive black holes to the complex interactions between galaxies and the intergalactic medium. In doing so, we will not only expand our understanding of the universe but also answer some of the most profound questions about the nature of space, time, and the forces that shape our reality. As we delve even deeper into the study of non-thermal radio galaxies, it becomes increasingly clear that their role in the universe is not just limited to providing insights into black holes or galaxy formation. These galaxies are fundamentally intertwined with some of the most profound questions in modern astrophysics. The study of their jets, lobes, and magnetic fields pushes the boundaries of our understanding about the very fabric of the universe. Through their behavior, we have the opportunity to study the behavior of matter and energy under extreme conditions that simply can't be replicated in laboratories here on Earth. One of the many compelling reasons to study non-thermal radio galaxies is their potential to reveal new physics. The high-energy environments around supermassive black holes are some of the most extreme conditions in the universe. Here, particles are accelerated to relativistic speeds, and magnetic fields are twisted and distorted in ways that we do not observe in more familiar environments. By understanding how matter behaves in these extreme conditions, we can probe the limits of known physics. In particular, these galaxies could provide insights into phenomena such as high-energy particle acceleration, magnetic field amplification, and even the behavior of quantum fields in curved spacetime. The study of non-thermal radio galaxies is also providing a window into the behavior of cosmic rays. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. They are produced in some of the most energetic events in the universe, including supernovae, gamma-ray bursts, and the jets of active galaxies. By studying the emissions from non-thermal radio galaxies, scientists can learn more about the origins and acceleration mechanisms of cosmic rays. The interaction between the jets and the intergalactic medium may play a significant role in the propagation and distribution of these particles, and by studying this interaction, researchers hope to answer critical questions about the nature and distribution of cosmic rays throughout the universe. But it's not just the extreme physics that makes non-thermal radio galaxies so fascinating. These galaxies also offer a unique opportunity to study the evolution of large-scale cosmic structures. The jets and lobes produced by these galaxies can span vast distances, sometimes extending millions of light-years from the galactic core. This means that they are not just small-scale phenomena, they have a profound impact on the larger cosmic environment. The way these jets interact with the surrounding intergalactic medium can affect the distribution of matter in galaxy clusters and even influence the formation of large-scale structures like superclusters and voids. The influence of non-thermal radio galaxies on their surroundings is often referred to as feedback. This feedback is a key component in galaxy evolution models, and it is believed to play a crucial role in regulating the growth of galaxies and clusters. When the powerful jets from these galaxies interact with the intergalactic medium, they inject energy into the surrounding gas, preventing it from cooling and condensing into new stars. This process helps to explain why some galaxies appear to be quenched and no longer form new stars. Understanding the feedback process in non-thermal radio galaxies is essential for developing a comprehensive model of galaxy formation and evolution. Moreover, this feedback is not just limited to the immediate surroundings of the galaxy. The energy injected by the jets can also have a broader impact on the larger-scale structure of the universe. For example, some scientists believe that the jets from non-thermal radio galaxies may play a role in the regulation of dark matter. Dark matter is the invisible substance that makes up a large portion of the universe's mass, but it does not interact with light, making it difficult to study directly. However, its gravitational influence on visible matter is profound. The feedback from the jets of non-thermal radio galaxies could potentially influence the distribution of dark matter in galaxy clusters and beyond, providing researchers with a new avenue for studying this elusive component of the universe. Interestingly, the interaction between these galaxies and the intergalactic medium also raises questions about the role of gas and dust in the formation of cosmic structures. The energy released by the jets can heat and disturb the gas in the surrounding regions, creating conditions that may prevent the formation of new stars. This process, called heating feedback, is believed to be a key factor in why some galaxies appear to be dead, that is, they no longer form stars. This feedback could be one of the reasons why the universe appears to have fewer star-forming galaxies than previously thought. In addition to its impact on galaxy formation and evolution, the study of non-thermal radio galaxies also provides a window into the broader dynamics of the universe. These galaxies are often located in the outskirts of galaxy clusters, where they interact with the vast stretches of intergalactic space. As the jets from these galaxies propagate through the intergalactic medium, they create large-scale shock waves that propagate outward. These shock waves are thought to play an important role in regulating the temperature and density of the gas and galaxy clusters, influencing the formation and evolution of galaxies within these clusters. By studying the interactions between non-thermal radio galaxies and their environment, researchers can better understand how large-scale cosmic structures form and evolve over time. This connection between the local environment of non-thermal radio galaxies and the larger cosmic structure highlights an important aspect of astrophysics: the interconnectedness of all things in the universe. Even the most distant and isolated objects, such as supermassive black holes and their associated galaxies, are part of a larger web of cosmic interactions. The feedback processes that occur in these galaxies ripple out through space, influencing the formation of galaxies, clusters, and even the distribution of dark matter. This interconnectedness underscores the complexity of the universe and the importance of studying these objects in a holistic manner. The role of non-thermal radio galaxies in the broader cosmic picture is just one part of a much larger narrative. As we continue to study these fascinating objects, we will uncover new layers of knowledge about the fundamental forces that shape the universe. With each new discovery, we move closer to answering some of the most profound questions in astrophysics. How do galaxies evolve? What drives the formation of jets and lobes? What is the true nature of dark matter and dark energy? And perhaps most intriguingly, what can non-thermal radio galaxies teach us about the fate of the universe itself? With the advent of more advanced observational techniques and the continued development of next-generation telescopes, the future of non-thermal radio galaxy research is incredibly promising. The discoveries we make today will lay the groundwork for future breakthroughs in our understanding of the cosmos. The mysteries surrounding these galaxies are vast and complex, but with each step we take toward unlocking those secrets, we are gaining a deeper understanding of the very nature of the universe. Non-thermal radio galaxies are not just distant and isolated objects. They are key players in the grand cosmic drama, shaping the universe as we know it. In the coming years, we can expect more breakthroughs that will challenge our current understanding of these galaxies. As our observational techniques improve and we continue to refine our models of galaxy formation, evolution, and feedback, we may discover that the universe is even more complex and interconnected than we ever imagined. These discoveries will not only advance our knowledge of the universe but may also have profound implications for our understanding of the fundamental laws of physics. As we look to the future, the study of non-thermal radio galaxies will remain one of the most exciting and important areas of research in astrophysics. The mysteries of these galaxies are far from being solved, and with every new observation, we are inching closer to uncovering the answers to some of the most profound questions in science. As we continue our exploration into the realm of non-thermal radio galaxies, one of the most striking aspects that emerges is the remarkable diversity within this category of galaxies. Non-thermal radio galaxies are not a single, homogeneous group. Rather, they exhibit a variety of different characteristics that make them unique. This diversity presents both a challenge and an opportunity for scientists seeking to understand the mechanisms at play within these enigmatic cosmic objects. The differences between various non-thermal radio galaxies can offer invaluable insights into the range of conditions under which these galaxies form, evolve, and interact with their environments. A key aspect of this diversity is the difference in the orientation of the jets relative to our line of sight. While many non-thermal radio galaxies display jets that appear to be pointed directly at us, others have their jets oriented at angles, or even perpendicular, to our view. This variation is crucial to understanding how the geometry of the galaxy and its environment influences the radiation we observe. Jets that are oriented directly towards us may appear brighter due to relativistic Doppler boosting, a phenomenon where the observed intensity of light is increased because the emitting source is moving towards us at high speeds. On the other hand, jets that are oriented away from us or at an angle may appear dimmer, with their emission being redshifted and spread out in different directions. These differences in the orientation of jets have far-reaching implications for our understanding of the physics behind non-thermal radio galaxies. By studying these galaxies from various angles, astronomers can gain insights into the mechanics of jet formation, the properties of the supermassive black holes that drive these jets, and the interactions between the jets and the surrounding gas. Moreover, understanding the orientation effects can help scientists refine their models of active galactic nuclei, AGN, and the processes that govern the behavior of supermassive black holes. Non-thermal radio galaxies can also be classified based on the presence of specific features in their radio emission. Some of these galaxies exhibit well-defined lobes that extend far from the galactic core, often spanning millions of light-years. These lobes are typically the result of powerful jets that push material out of the galaxy and into the surrounding intergalactic medium. Other galaxies, however, may have smaller or less pronounced lobes, or they might exhibit a more diffuse radio emission that suggests a less energetic jet system. The difference in the size and structure of the lobes is another indicator of the underlying processes at play within the galaxy, and it provides crucial information about the energy output of the jets and their interaction with the surrounding environment. In some cases, the lobes of non-thermal radio galaxies appear to be somewhat irregular or distorted. This can occur when the galaxy's motion through the intergalactic medium causes the jets to bend or deflect. This phenomenon, known as ram pressure stripping, occurs when the pressure exerted by the surrounding gas on the galaxy's jets causes them to change direction or morphology. This interaction can lead to the formation of complex, twisted structures in the lobes, revealing the dynamic nature of the galaxy's environment. The study of such irregularities provides valuable insights into the mechanisms that shape the evolution of these objects and their role within the larger cosmic framework. In addition to their morphological diversity, non-thermal radio galaxies are also varied in terms of their spectral properties. The spectrum of radiation emitted by these galaxies spans a wide range of wavelengths, from low-frequency radio waves to high-energy X-rays and gamma rays. The emission from non-thermal radio galaxies is often dominated by synchrotron radiation, a type of radiation produced by charged particles moving at relativistic speeds in a magnetic field. However, depending on the energy of the particles and the strength of the magnetic fields, the spectrum can vary significantly. Some non-thermal radio galaxies exhibit a flat spectrum, meaning that the intensity of the radiation remains relatively constant across a wide range of frequencies. This flat spectrum is often associated with regions of the galaxy where the jet is producing a large amount of radiation at a relatively uniform rate. Other galaxies, however, may show a steep spectrum, indicating that the emission is dominated by lower energy particles or that the jet is losing energy as it propagates outward. The spectral properties of non-thermal radio galaxies provide crucial information about the energy distribution of the particles in the jet and the strength of the magnetic fields present in the galaxy. Another intriguing aspect of non-thermal radio galaxies is the way in which their jets interact with the surrounding intergalactic medium. As the jets propagate through the relatively empty space of the intergalactic medium, they can produce large-scale shock waves that propagate outward, heating the surrounding gas and creating complex structures. These shock waves, known as bow shocks, are similar to the shock waves produced by supersonic objects moving through air on Earth. However, in the case of non-thermal radio galaxies, the shock waves are produced by highly energetic jets moving through the tenuous gas of the intergalactic medium. The formation of bow shocks can lead to a variety of interesting phenomena. For example, the shock waves can compress the gas in the surrounding environment, triggering the formation of new stars or causing existing stars to evolve more rapidly. Additionally, the energy deposited by the shock waves can influence the dynamics of galaxy clusters, preventing the gas from cooling and condensing into new stars. This process, known as heating feedback, is believed to play a significant role in regulating the growth of galaxies and clusters, helping to explain why some galaxies appear to be quenched and no longer form stars. In some cases, the jets of non-thermal radio galaxies can also interact with the cosmic microwave background (CMB) radiation, the faint afterglow of the Big Bang. The CMB is a relic of the early universe, and it provides a faint but ubiquitous source of radiation that fills the entire cosmos. When the relativistic jets from non-thermal radio galaxies travel through this radiation, they can experience a process known as the inverse Compton effect. In this process, the high-energy electrons in the jet collide with the low-energy photons from the CMB, transferring energy and producing high-energy X-rays and gamma rays. This interaction can significantly alter the spectrum of the galaxy's radiation and is a key diagnostic tool for understanding the nature of the jets and the particles within them. The study of non-thermal radio galaxies also has important implications for our understanding of the large-scale structure of the universe. These galaxies are often found at the centers of galaxy clusters, and the interactions between their jets and the intergalactic medium can have a significant impact on the evolution of these clusters. The energy injected by the jets can prevent the gas in the cluster from cooling and condensing, thereby inhibiting the formation of new stars. This feedback process plays a crucial role in regulating the growth of galaxies within clusters and may be responsible for the observed red and dead nature of some galaxies in these environments. At the same time, the study of non-thermal radio galaxies offers a unique opportunity to probe the properties of the intergalactic medium itself. The jets from these galaxies can travel vast distances through the diffuse gas between galaxies, providing a snapshot of the conditions in this largely unexplored region of space. By studying how the jets interact with the surrounding medium, scientists can learn more about the density, temperature, and composition of the gas, as well as its role in the formation of galaxies and galaxy clusters. Ultimately, the study of non-thermal radio galaxies offers a powerful tool for understanding the complex and dynamic processes that govern the universe. These galaxies are not just interesting in their own right, they are essential to our understanding of the fundamental forces that shape the cosmos. By continuing to observe and study these fascinating objects, we can unlock new insights into the nature of dark matter, the evolution of galaxies, and the mechanisms that drive cosmic growth. Every discovery about non-thermal radio galaxies brings us closer to understanding the most fundamental questions in astrophysics. How do supermassive black holes shape the structure of galaxies? What role do cosmic feedback processes play in regulating galaxy formation and evolution? How does the interplay between galaxies, clusters, and the intergalactic medium affect the large-scale structure of the universe? The answers to these questions lie within the heart of non-thermal radio galaxies, and as we continue to investigate these cosmic enigmas, we are sure to uncover new and unexpected revelations about the universe itself. As we delve further into the complexities of non-thermal radio galaxies, it becomes clear that their study reveals much more than just the behavior of distant cosmic phenomena. These galaxies also offer a deeper insight into the fundamental forces that govern the universe at the most extreme scales. While much of the attention surrounding non-thermal radio galaxies focuses on their dramatic jets and luminous emissions, these objects are also crucial for understanding the evolution of the large-scale structures of the universe itself. One particularly intriguing feature of non-thermal radio galaxies is the apparent connection between their activity and the large-scale environment in which they reside. The supermassive black holes at the centers of these galaxies are thought to play a key role in driving the jets that are observed at radio wavelengths. These black holes are typically surrounded by accretion disks, which consist of gas and dust that is gradually spiraling inwards due to the immense gravitational pull of the black hole. As the material in the accretion disk is pulled closer to the black hole, it becomes increasingly heated and accelerated to relativistic speeds, generating a wealth of radiation that is emitted across the electromagnetic spectrum, including at radio wavelengths. The feedback mechanisms that govern the interaction between the supermassive black hole and the surrounding galaxy can have profound consequences for the larger environment. As the supermassive black hole accretes material from the surrounding gas, the energy produced by the infall of this material can drive powerful outflows, in the form of relativistic jets. These jets not only heat the surrounding gas but also push large amounts of it out of the galaxy, preventing the cooling of the gas and inhibiting the formation of new stars. This process, known as AGN feedback, plays a critical role in regulating the star formation rate in galaxies, and it is believed to be an essential driver of the evolution of galaxies across cosmic time. Interestingly, these feedback processes are not limited to the host galaxy itself. The energy injected by the supermassive black hole can have far-reaching effects on the intergalactic medium. As the relativistic jets from non-thermal radio galaxies propagate through the vast voids of space, they interact with the gas between galaxies, creating a series of shock waves and disturbances that can influence the formation and evolution of galaxy clusters. The hot gas that is expelled by these jets may prevent the cooling of the cluster's gas, stifling the formation of new stars and regulating the growth of the cluster's galaxies. This complex interplay between galaxies, black holes, and the intergalactic medium is one of the key areas of study in modern cosmology, as it helps to explain many of the observed features of galaxy clusters, including the red and dead population of galaxies that are found in these environments. The impact of non-thermal radio galaxies extends even further, influencing the structure of the universe on the largest scales. When we observe clusters of galaxies, we often see a variety of different objects, from bright, star-forming galaxies to more passive systems that no longer produce new stars. One of the key factors that shape this diversity is the process of cosmic feedback, which can be traced back to the activity of supermassive black holes in non-thermal radio galaxies. The energy injected by these black holes, through the formation of jets and the expulsion of gas, can prevent the cooling of the intracluster medium, which in turn suppresses star formation. As a result, galaxies and clusters may evolve more slowly than their counterparts in the field, becoming redder and less active over time. The relationship between non-thermal radio galaxies and the intergalactic medium also sheds light on the properties of the so-called cosmic web, the large-scale structure of the universe. The cosmic web is composed of vast filaments of dark matter and gas, which connect galaxy clusters and form a network of structures that spans the entire observable universe. The activity of non-thermal radio galaxies, with their powerful jets and feedback mechanisms, plays a crucial role in shaping the dynamics of this cosmic web. The energy produced by these galaxies can drive the motion of gas within the web, influencing the formation of new galaxies and the evolution of existing ones. One of the most profound implications of studying non-thermal radio galaxies is the insight it provides into the role of dark matter in shaping the structure of the universe. Dark matter, which constitutes a significant portion of the total mass in the universe, is thought to play a central role in the formation of galaxies and galaxy clusters. Although we cannot observe dark matter directly, its presence can be inferred through its gravitational effects on visible matter. The interactions between non-thermal radio galaxies and the cosmic web of dark matter and gas offer a unique opportunity to probe the properties of dark matter and its influence on the evolution of the universe. The phenomenon of non-thermal radio emission is also a valuable tool for investigating the nature of relativistic particles and magnetic fields in the universe. The synchrotron radiation produced by these galaxies is a direct result of the motion of charged particles and magnetic fields, and by studying this radiation, scientists can gain a better understanding of the properties of both the particles and the fields. This has important implications for our understanding of high-energy astrophysics, as it allows researchers to study the behavior of particles moving at speeds close to the speed of light, as well as the strength and structure of the magnetic fields that govern their motion. The study of non-thermal radio galaxies has far-reaching implications not just for our understanding of the distant universe, but also for our understanding of fundamental physics. These galaxies provide a unique environment in which to study relativistic jets, supermassive black holes, and the behavior of particles in extreme conditions. The insights gained from this research can help to inform theories about the nature of black holes, the behavior of matter under extreme conditions, and the role of cosmic feedback in shaping the universe on large scales. As our observational techniques continue to improve, and as new telescopes and instruments come online, our understanding of non-thermal radio galaxies will continue to grow. Instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, the Square Kilometer Array, SK, and the upcoming James Webb Space Telescope, JWST, will allow scientists to probe the properties of these galaxies in unprecedented detail. These observations will help to answer some of the most fundamental questions in astrophysics, including the nature of dark matter, the behavior of supermassive black holes, and the processes that govern the formation and evolution of galaxies. Non-thermal radio galaxies are far more than just a fascinating feature of the universe's cosmic landscape. They are fundamental to our understanding of the large-scale structure of the universe, the role of dark matter, the dynamics of galaxy clusters, and the behavior of matter in extreme environments. By continuing to study these galaxies, we can unlock new insights into the nature of the cosmos itself, gaining a deeper understanding of the forces and phenomena that shape the universe on the grandest scales. As we continue exploring the role of non-thermal radio galaxies in the broader context of cosmic evolution, it's important to consider the tools and methods that enable scientists to study these distant objects in such remarkable detail. The advancement of radio astronomy, in particular, has been a game-changer for understanding these enigmatic systems. The ability to observe the universe at radio wavelengths allows astronomers to peer through dust clouds that obscure our view in optical wavelengths, revealing the true structure and dynamics of distant galaxies. This is where the power of radio telescopes comes into play. Radio telescopes, such as the Very Large Array, VLA, and the upcoming Square Kilometer Array, SKA, are essential for observing the faint, distant emissions from non-thermal radio galaxies. These instruments can detect the weak signals emitted by synchrotron radiation, the hallmark of non-thermal emission, which can originate from extremely distant galaxies. By capturing the faint radio waves emitted from these galaxies, scientists can build a picture of their physical characteristics, such as the size of the jets, the strength of the magnetic fields, and the energy of the relativistic particles responsible for the emission. One of the most important aspects of studying non-thermal radio galaxies through radio telescopes is the ability to map out the structure of their jets and lobes in great detail. The jets of non-thermal radio galaxies are vast, often stretching hundreds of thousands of light-years across space. By observing these jets in radio wavelengths, scientists can trace their evolution and understand the mechanisms driving their formation. The jets are often aligned along the axis of the supermassive black hole at the galaxy's center, and their morphology provides important clues about the processes occurring near the black hole, such as the interaction between the accretion disk and the surrounding material. In addition to mapping out the structure of the jets, radio telescopes also allow scientists to study the physical properties of the gas surrounding these galaxies. This gas, often in the form of a hot, ionized plasma, is key to understanding how non-thermal radio galaxies interact with their environment. The jets and lobes of these galaxies can transfer vast amounts of energy into the surrounding gas, heating it up and causing it to expand. The interaction between the jets and the intergalactic medium is a crucial aspect of the feedback processes that govern galaxy evolution. By studying the radio emission from these regions, astronomers can learn more about the temperature, density, and composition of the gas, as well as the strength of the magnetic fields that are present. One of the biggest mysteries surrounding non-thermal radio galaxies is the exact mechanism by which the relativistic jets are formed and accelerated. While much has been learned about the behavior of these jets, there are still many unanswered questions about the physical processes that drive their formation. For instance, how is the energy from the accretion disk channeled into the jets? What role do magnetic fields play in focusing and accelerating the particles within the jets? How do the jets manage to extend across such vast distances, often several orders of magnitude larger than the host galaxy itself? To answer these questions, scientists have developed a number of theoretical models that attempt to explain the formation and acceleration of relativistic jets in non-thermal radio galaxies. One of the most widely accepted models is the Blandford's Najek mechanism. which proposes that the energy needed to power the jets is extracted from the rotating supermassive black hole through a process known as electromagnetic extraction. According to this model, the black hole's spin creates a powerful magnetic field, which can accelerate particles to relativistic speeds and propel them outwards along the rotational axis of the black hole. This mechanism provides a plausible explanation for the formation of jets, although there is still much to be learned about the detailed physics behind the process. Another important question in the study of non-thermal radio galaxies is the role of turbulence in the formation and evolution of jets. The material surrounding the supermassive black hole is often highly turbulent, with chaotic flows of gas and magnetic fields. Some researchers believe that turbulence plays a key role in generating the energetic particles that power the jets. In this view, the turbulence creates regions of high pressure and magnetic energy, which can accelerate particles to relativistic speeds. This mechanism may be especially important in galaxies with active star formation, where the surrounding gas is more turbulent and the conditions for jet formation are more favorable. The energy budget of non-thermal radio galaxies is another fascinating aspect of their study. The jets of these galaxies can release an enormous amount of energy, sometimes equivalent to the energy produced by an entire galaxy's worth of stars. This energy is distributed across the electromagnetic spectrum, from radio wavelengths all the way to high-energy X-rays and gamma rays. The fact that non-thermal radio galaxies can generate such vast amounts of energy raises important questions about the efficiency of the processes that power these jets. How much of the energy from the accretion disk is converted into relativistic particles, and how much is lost in the form of radiation? Are there other, as yet unknown mechanisms that contribute to the energy budget of these galaxies? The study of non-thermal radio galaxies is also deeply intertwined with the study of cosmic evolution. These galaxies are not just isolated objects but rather are deeply connected to the larger structure of the universe. The energy they release into their surroundings can have significant effects on the evolution of the intergalactic medium, the formation of new galaxies, and the growth of galaxy clusters. In fact, some researchers believe that the feedback from active galaxies like non-thermal radio galaxies may be a major factor in regulating the growth of large-scale cosmic structures. In the context of galaxy clusters, for instance, the feedback from non-thermal radio galaxies is believed to play a crucial role in preventing the overcooling of the intra-cluster medium. The hot gas that fills these clusters can cool over time, eventually leading to the formation of new stars. However, the energy released by the jets of non-thermal radio galaxies can prevent this cooling, keeping the gas from collapsing and forming stars. This process, known as heating or feedback, is thought to be responsible for the observed red and dead galaxies in the cores of galaxy clusters, galaxies that are no longer forming stars and are instead evolving into passive systems. Another important aspect of the study of non-thermal radio galaxies is their relationship with other types of active galactic nuclei, AGN. While non-thermal radio galaxies are just one subclass of AGN, they share many similarities with other types, such as Seyfert galaxies and quasars. All of these objects are powered by supermassive black holes at their centers, and all exhibit strong, high-energy emissions across the electromagnetic spectrum. However, non-thermal radio galaxies are distinguished by their powerful radio jets, which are much more prominent than in other types of AGN. The classification of AGN is an ongoing area of research, and scientists are continually refining their understanding of the different types of active galaxies and the mechanisms that power them. One of the key challenges in this field is the diversity of AGN, which can vary widely in terms of their luminosity, morphology, and the strength of their radio emissions. As astronomers continue to gather more observational data from radio telescopes and other instruments, they will be able to refine their models of AGN and gain a more complete understanding of how these objects evolve over time. Non-thermal radio galaxies are among the most fascinating and mysterious objects in the universe. Their study offers profound insights into the nature of supermassive black holes, relativistic jets, and the feedback processes that govern the evolution of galaxies. As our observational capabilities continue to improve, we are likely to uncover even more surprising discoveries about these enigmatic objects and their role in the larger cosmic ecosystem. With each new breakthrough in radio astronomy, we come one step closer to understanding the forces that shape the universe and the fundamental physics that govern the behavior of matter and energy on the most extreme scales. Let's take a deeper dive into how the surrounding environment of these galaxies interacts with their jets, and how this interaction may influence both their behavior and the broader cosmic landscape. The gas and dust surrounding these galaxies can play an essential role in shaping the final observed morphology and behavior of the jets. One of the key interactions between the jets of non-thermal radio galaxies and their surroundings involves the phenomenon known as shock waves. As the relativistic jets rush through the surrounding gas, they can generate shock waves, much like a sonic boom that occurs when an object travels faster than the speed of sound. These shock waves can have profound effects on the intergalactic medium, compressing the gas and causing it to heat up. This heating can prevent the gas from cooling too rapidly, which can help maintain the stability of the surrounding galaxy and prevent excessive star formation. This process of heating, or feedback, is a crucial aspect of galaxy evolution. These shock waves also interact with the dense clouds of gas and dust that may surround the central black hole. When the jets of a non-thermal radio galaxy collide with this gas, they can create vast cavities, or bubbles, within the surrounding medium. These bubbles, which can extend over vast distances, can have significant consequences for the galaxy's evolution. The energy injected by the jets can influence the formation of new stars, the dynamics of gas clouds, and even the large-scale structure of galaxy clusters. In some cases, these jets may even drive gas out of the galaxy entirely, a process known as galactic winds, which can reduce the available gas supply for future star formation. The study of these interactions is crucial for understanding how non-thermal radio galaxies affect their environments and contribute to the overall evolution of galaxies. In some cases, the impact of the jets may even help prevent the formation of new stars, leading to the observed phenomenon of passive galaxies and galaxy clusters. These galaxies, which are no longer actively forming stars, may have their star formation quenched by the energetic feedback from their central supermassive black holes, including non-thermal radio galaxies. Another important aspect of non-thermal radio galaxies is the potential role they play in the broader context of the intergalactic medium. As we mentioned earlier, these galaxies inject vast amounts of energy into the surrounding gas, creating shock waves and heating the intergalactic medium. Over time, this energy can have a significant impact on the evolution of the universe's large-scale structure. One of the key challenges in cosmology is understanding how galaxies interact with the gas that fills the vast spaces between them, known as the intergalactic medium, and how this interaction influences the formation of galaxy clusters and superclusters. In the case of non-thermal radio galaxies, the energy they release into the surrounding medium can affect the formation of large-scale structures, influencing the distribution of galaxies across the cosmos. The interaction between these galaxies and the intergalactic medium may also provide important insights into the processes that govern the formation and evolution of galaxy clusters. In some cases, the energetic feedback from the jets of non-thermal radio galaxies may help regulate the growth of these clusters, preventing excessive cooling and maintaining the stability of the gas within them. It is also worth noting that the study of non-thermal radio galaxies has important implications for our understanding of dark matter and dark energy. While dark matter and dark energy remain some of the most elusive and mysterious components of the universe, understanding how they interact with normal matter can provide crucial clues about their nature. The feedback processes from non-thermal radio galaxies, which can have far-reaching effects on the intergalactic medium and the formation of large-scale structures, may offer indirect insights into the role that dark matter and dark energy play in the evolution of the universe. In addition to their impact on galaxy evolution, non-thermal radio galaxies also serve as natural laboratories for studying extreme physical processes. The extreme conditions present in the environments around supermassive black holes, such as intense gravitational fields, high temperatures, and powerful magnetic fields, provide a unique opportunity to test our understanding of fundamental physics. For example, non-thermal radio galaxies offer a chance to study relativistic jets in environments where the effects of gravity and magnetism are at their most extreme. These observations may lead to new insights into the behavior of matter and energy under the most extreme conditions in the universe, offering valuable data for both theoretical and observational cosmology. Another fascinating aspect of non-thermal radio galaxies is their potential to serve as a tool for studying the expansion of the universe. By observing the radio emissions from distant galaxies, astronomers can gain valuable insights into the history of cosmic expansion. The way in which the jets of non-thermal radio galaxies interact with the surrounding gas can be influenced by the expansion of the universe, providing important clues about the rate of expansion and the behavior of the universe over cosmic time scales. As astronomers gather more data from radio telescopes and other observatories, they may be able to refine their models of cosmic expansion and gain a more detailed understanding of the forces that have shaped the universe since the Big Bang. As we explore the role of non-thermal radio galaxies in the context of cosmology, it is essential to consider the advancements in technology that have allowed us to study these distant objects in such detail. The next generation of radio telescopes, such as the Square Kilometre Array, SKA, will provide unprecedented capabilities for studying non-thermal radio galaxies. The SKA, with its enormous collecting area and sensitivity, will be able to observe galaxies at much greater distances and with much greater detail than ever before. This will open up new possibilities for studying the physical processes that drive the formation of relativistic jets, as well as the evolution of galaxies and galaxy clusters. In particular, the SKA will enable scientists to observe the faint radio emissions from the earliest stages of galaxy formation, providing new insights into the role of non-thermal radio galaxies in the early universe. These observations will also shed light on the feedback processes that regulate the growth of galaxies and clusters, helping us understand how large-scale structures have evolved over cosmic time. The SKA's ability to observe galaxies across a wide range of wavelengths, from low-frequency radio waves to higher-frequency emissions, will allow astronomers to piece together a more complete picture of the physical processes that govern the universe's evolution. Looking ahead, the continued study of non-thermal radio galaxies promises to reveal even more exciting discoveries about the universe. As our understanding of these enigmatic objects deepens, we may uncover new aspects of galaxy formation, supermassive black hole growth, and cosmic evolution that were previously beyond our reach. With each new discovery, we move closer to understanding the true nature of the universe and the fundamental forces that shape it. Non-thermal radio galaxies represent one of the most intriguing and complex phenomena in the cosmos. Their study offers unique insights into the behavior of supermassive black holes, the nature of relativistic jets, and the processes that drive galaxy evolution. Through the use of advanced radio telescopes and cutting-edge observational techniques, scientists continue to uncover the mysteries of these distant and powerful galaxies. As our technology advances and our understanding of the universe deepens, the role of non-thermal radio galaxies in shaping the cosmos will become clearer, offering a wealth of new opportunities for discovery in the years to come. The journey into the world of non-thermal radio galaxies is far from over, as there is still much to uncover about these fascinating cosmic phenomena. Beyond the immediate physical effects of relativistic jets and their interaction with the surrounding gas, there are other critical aspects of their behavior that continue to challenge our understanding of the universe. One area that has garnered increasing attention is the connection between non-thermal radio galaxies and the formation of supermassive black holes. These enigmatic objects, which reside at the centers of many galaxies, are thought to play a crucial role in the growth and evolution of their host galaxies. But how exactly do these black holes grow to such enormous sizes, and what factors influence their development? Non-thermal radio galaxies may hold some of the answers. The formation of supermassive black holes is a topic that has been widely debated among astrophysicists. Some theories suggest that these black holes may have formed early in the history of the universe, possibly as a result of the collapse of massive gas clouds in the early stages of galaxy formation. Others propose that supermassive black holes may grow over time through the accumulation of gas and dust, feeding on the material around them in a process known as accretion. In the case of non-thermal radio galaxies, the existence of powerful jets emanating from the supermassive black holes at their centers provides a fascinating clue. These jets, which are composed of highly energetic particles, are thought to be a direct result of the accretion process. As matter falls into the black hole, it is heated to extreme temperatures and accelerated to relativistic speeds, creating the jets that we observe in the radio wavelengths. But the question remains, what factors influence the size and power of these jets? How do they grow so large and powerful, reaching across vast distances and influencing the surrounding environment? One possibility is that the magnetic fields associated with the black holes play a key role in shaping the jets. As material falls into the black hole, it is thought that the intense magnetic fields can channel the material into narrow, focused beams that are ejected at relativistic speeds. The strength and configuration of these magnetic fields can have a significant impact on the size and direction of the jets, helping to explain the vast variety of jet structures observed in non-thermal radio galaxies. The nature of these magnetic fields, and their interaction with the surrounding environment, is an area of intense research. Some scientists have proposed that the magnetic fields around supermassive black holes could be generated by processes that occur deep within the black hole's accretion disk. These processes may involve the twisting and stretching of magnetic field lines as the material in the disk moves inward toward the black hole. This twisting and stretching can amplify the magnetic fields to the point where they can accelerate particles to relativistic speeds, creating the powerful jets that are characteristic of non-thermal radio galaxies. The magnetic fields around black holes are also thought to be responsible for the collimation, or focusing, of the jets. Without these magnetic fields, the jets would likely disperse into the surrounding gas, losing their coherence and power. By tightly constraining the flow of material into narrow beams, the magnetic fields ensure that the jets retain their structure and energy over vast distances. This process of collimation is crucial for understanding the observed morphology of non-thermal radio galaxies, where the jets can extend for millions or even billions of light years. Interestingly, the study of the magnetic fields in non-thermal radio galaxies also has broader implications for our understanding of other astrophysical phenomena, such as gamma-ray bursts, active galactic nuclei, AGN, and even the behavior of matter in the extreme environments near black holes. The processes that govern the formation and behavior of relativistic jets are not unique to radio galaxies. They are thought to be common to a variety of high-energy phenomena in the universe. By studying non-thermal radio galaxies, scientists can gain insights into the mechanisms that drive these cosmic events and improve our understanding of the fundamental physics at play. Beyond the immediate realm of galaxy evolution and jet formation, non-thermal radio galaxies also offer a window into the larger-scale structure of the universe. These galaxies, with their powerful jets and energetic feedback mechanisms, play a significant role in shaping the cosmic web, the vast network of galaxy clusters, superclusters, and voids that make up the large-scale structure of the universe. The energy injected by the jets of non-thermal radio galaxies can influence the dynamics of these structures, helping to regulate the formation and growth of galaxies and clusters over cosmic time. For example, the feedback from non-thermal radio galaxies can affect the temperature and density of the gas within galaxy clusters. As jets from the central black holes inject energy into the surrounding medium, they can heat up the gas, preventing it from cooling too rapidly. This process is thought to play a key role in the maintenance of the hot gas that fills galaxy clusters, a crucial component of the overall structure of these clusters. Without this heating, the gas would cool and condense, potentially triggering excessive star formation and disrupting the delicate balance of the cluster. The study of non-thermal radio galaxies has also provided new insights into the large-scale magnetic fields that permeate the universe. These magnetic fields, which are thought to be generated by the motion of charged particles within galaxies and galaxy clusters, are believed to play a significant role in shaping the evolution of the cosmos. By examining the radio emissions from non-thermal radio galaxies, scientists can gain valuable information about the strength, orientation, and distribution of these magnetic fields on cosmological scales. This, in turn, may help to explain the behavior of the intergalactic medium and the formation of large-scale structures in the universe. Another intriguing aspect of non-thermal radio galaxies is their potential to influence the formation of new galaxies. The powerful jets from supermassive black holes can have a profound impact on the surrounding gas, driving it away from the galaxy and preventing it from collapsing into new stars. This process, known as feedback, can regulate the rate of star formation within galaxies and influence the overall evolution of the galaxy population. In some cases, the energetic feedback from non-thermal radio galaxies may even halt star formation altogether, leading to the creation of dead, or passive, galaxies that no longer form new stars. Moreover, the interplay between the jets of non-thermal radio galaxies and their environment may help to shape the distribution of galaxies across the universe. The energy injected by these jets can prevent gas from cooling and collapsing into new stars, influencing the overall rate of galaxy formation in different regions of the universe. In some cases, this process may lead to the formation of large galaxy clusters, where galaxies are packed together in a dense, gravitationally bound structure. The feedback from non-thermal radio galaxies may play a role in maintaining the stability of these clusters, regulating the formation of new galaxies and influencing the distribution of matter within them. The study of non-thermal radio galaxies offers a wealth of opportunities to explore some of the most fundamental questions in astrophysics. These galaxies, with their powerful jets and energetic feedback processes, provide valuable insights into the nature of supermassive black holes, galaxy evolution, and the large-scale structure of the universe. As our observational techniques continue to improve, and as new technologies like the square-kilometer array come online, we can expect to uncover even more exciting discoveries about these fascinating cosmic objects. Non-thermal radio galaxies continue to provide a fascinating look into some of the most powerful and mysterious phenomena in the universe. As we peel back the layers of their complexities, it becomes clear that these galaxies serve as an essential piece of the puzzle in understanding cosmic evolution, black hole physics, and the larger-scale structure of the universe. One of the most exciting aspects of studying non-thermal radio galaxies is the way in which they illuminate the physics of extreme environments. The supermassive black holes at their cores generate an intense gravitational field, bending space and time in ways that challenge our understanding of the laws of physics. These black holes, some of the largest known, are capable of generating enormous amounts of energy, much of which is ejected in the form of relativistic jets. This process of energy extraction from a black hole is an area of intense study and may reveal fundamental insights into the mechanics of black hole accretion disks, the behavior of matter under extreme conditions, and the interaction between the strong gravitational fields and the surrounding gas. It's important to remember that non-thermal radio galaxies are not just static objects, they are constantly evolving. The jets emitted by their central black holes evolve over time, growing larger and more energetic, or sometimes shrinking as their energy dissipates into the surrounding medium. This variability is due in part to the complex dynamics of accretion and jet formation. The material that feeds into a black hole is not always uniform, and fluctuations in the supply of gas can cause the jets to undergo dramatic changes in size and power. Sometimes, these jets can become quieter and less energetic, only to flare up again as new material falls into the black hole and is rapidly accelerated. This variability offers a dynamic perspective on the role that non-thermal radio galaxies play in their environments. Unlike simpler celestial objects, their energy output and interactions with the surrounding intergalactic medium are not constant, and these fluctuations are key to understanding the long-term evolution of galaxies, star formation, and even the large-scale structure of the universe. These jets are composed of highly energetic particles that travel at relativistic speeds, often approaching the speed of light. These particles, primarily electrons, are accelerated in the presence of magnetic fields around the black hole. However, the exact process by which this acceleration occurs remains a topic of great debate. One potential mechanism is the presence of shockwaves created by the jets as they interact with the surrounding material. These shockwaves can compress the surrounding gas, creating high-energy environments where particles can be accelerated to relativistic speeds. In some cases, the jets themselves may also serve as particle accelerators, further boosting the energy of the particles they contain. As these jets travel outward from the black hole, they can interact with the surrounding gas and even with other galaxies. In some cases, the jets may be strong enough to disrupt the intergalactic medium, injecting energy into the gas and preventing it from cooling and forming new stars. This feedback mechanism, known as radio mode feedback, can significantly influence the star formation rates of galaxies within clusters. By injecting heat into the gas, the jets can prevent it from cooling and collapsing into new stars, thereby regulating the overall growth of the galaxy. One of the most striking features of non-thermal radio galaxies is their immense size. Some of these jets can extend hundreds of thousands, or even millions, of light years from the galactic center. This vast reach is a direct result of the power of the jets, and the immense energy being released from the black hole. As the jets travel outward, they can interact with the surrounding gas, creating large shockwaves and expanding the gas around them. These interactions can lead to the formation of vast radio lobes, the large, diffuse regions of radio-emitting gas that are observed around many non-thermal radio galaxies. These lobes are one of the key features that set non-thermal radio galaxies apart from other types of galaxies, making them some of the most remarkable objects in the universe. Interestingly, the radio lobes that form around these galaxies are not just empty space. They are filled with high-energy particles, magnetic fields, and hot gas. As the jets propagate outward, they can compress and heat the surrounding gas, creating regions of intense radiation. In some cases, these radio lobes can contain more energy than the galaxy itself, providing a fascinating glimpse into the amount of power that is involved in these cosmic phenomena. The material within the lobes is also thought to be highly magnetized, and the radio emission from these regions is primarily a result of synchrotron radiation, where charged particles spiral around magnetic field lines and emit radiation. A key question that arises when studying the vast radio lobes of non-thermal radio galaxies is how the energy within these regions is distributed. How do these enormous structures maintain their energy over such vast distances? One possible explanation is the presence of a continuous supply of energy from the black hole itself. As the black hole accretes material, it may continually feed the jets, allowing them to maintain their power over time. This continuous supply of energy could help to explain the persistent nature of the radio lobes, as well as their immense size. Furthermore, as the jets move through the intergalactic medium, they can create large shockwaves and turbulence that further disrupt the surrounding gas. This turbulent environment can lead to the formation of complex structures, such as filaments and bubbles, within the radio lobes. These structures are often seen in high-resolution images of non-thermal radio galaxies, providing further insight into the complex dynamics of these systems. At the same time, these shocks can also accelerate particles to incredibly high energies, creating a vast reservoir of cosmic rays. These cosmic rays are some of the highest energy particles in the universe, and are thought to play a key role in the intergalactic medium. The presence of cosmic rays in the vicinity of non-thermal radio galaxies could help to explain the observed cosmic ray background, as well as the propagation of these particles across vast distances. While the study of non-thermal radio galaxies has yielded many insights, there is still much to learn. One of the biggest challenges facing astronomers is how to observe these galaxies in sufficient detail to fully understand the processes that govern their behavior. Despite the advances in radio astronomy, the study of non-thermal radio galaxies requires the use of specialized instruments and techniques to probe their jets, lobes, and surrounding environments. The advent of new technologies, such as the square-kilometer array and the next-generation radio telescopes, will undoubtedly provide astronomers with the tools they need to continue exploring these fascinating objects. In the future, we may also see more detailed studies of the polarization of radio emissions from non-thermal radio galaxies. Polarization is a key tool for studying the magnetic fields in these galaxies and understanding how they influence the formation of jets and lobes. By studying the polarization patterns of radio emissions, astronomers can gain insights into the structure of the magnetic fields around black holes, as well as the dynamics of the jets and lobes. Theoretical models are also crucial in providing a framework for understanding the observed phenomena. While the mechanisms behind the formation and behavior of non-thermal radio galaxies are well established, there are still many unanswered questions. Researchers are continuing to refine their models of black hole accretion, jet formation, and magnetic field dynamics to gain a more complete picture of these galaxies and their role in the cosmos. Moreover, future observations may help to further elucidate the connection between non-thermal radio galaxies and the larger structure of the universe. These galaxies play a key role in shaping the cosmic web, and their feedback mechanisms can influence the formation and evolution of galaxies on cosmological scales. By studying the interactions between non-thermal radio galaxies and the gas that surrounds them, we can gain a better understanding of the processes that regulate galaxy formation and growth over cosmic time. Non-thermal radio galaxies are not just an interesting anomaly in the cosmos, they are essential to our understanding of the universe. These galaxies, with their powerful jets, massive black holes, and vast radio lobes, offer insights into the most extreme environments in the universe. By studying non-thermal radio galaxies, astronomers are able to probe the behavior of matter under extreme conditions, investigate the formation of supermassive black holes, and gain a deeper understanding of the forces that shape the evolution of galaxies and the structure of the universe. As our observational tools and theoretical models continue to improve, the mysteries of non-thermal radio galaxies will undoubtedly reveal even more about the nature of the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.